Hi, everyone. So the way we did this was everything is pre-recorded. In fact, I don't yet see Daniel having joined, and he would be presenting first. So we're here for Q&A. I will certainly be checking the chat room on the VFairs site periodically throughout the entire conference if anyone has questions. But otherwise, feel free to ask if you have any questions. The other thing is I noted on the VFairs chat room, the videos are not ordered. We uploaded them with part numbers, and those seem to have gotten stripped off and names changed a bit. So I put the correct order in the VFairs room. If you're accessing through the Whova app, they seem to be numbered and I think in the right order. I didn't actually watch all of them yet. A quick look at the slide suggested that they were. Aha. Hi, Daniel.
Hey, John. So I guess I don't really know how this should be set up. If anyone has questions, we could go ahead and answer them. Otherwise, I guess there's a way to play the videos. And if people have questions, we'll pause it every once in a while. People can ask questions, or people can ask questions as the video plays. You can do that. Once I actually. Do people have any questions? Guess not. John, do you know how you can play the videos? Or do you just play it as part of the Zoom?
That I haven't figured out. So that's really up to what the people here want, and we can play them by screen sharing. There's a comment in chat. Question of sketching time series data. I think need to ask to be a bit more specific on what type of sketching of time series data.
Yeah, I don't think we have anything very specific to time series data. But I think in the production system, there's some stuff where there is a time component, which is relevant for
So Daniel, your video seems to be moving very, very slowly, and your audio was breaking up. I will message you outside the app. Uh-oh, I think we lost Daniel. Oh, don't know if I have his number in here right now. Okay, can't find his phone number right now. Okay, so I'm not sure how people do this. We can play the videos if people are interested in that. Please make a comment if that's what you're expecting. Either unmute yourself and make the comment or in chat. Okay, the answer. Okay, we can play videos. I will work on getting that going. Give me a few moments. Need to share screen. Okay, it started playing locally before I had the chance to share. There we go, share screen. Okay, hope everyone can see this. And let's get started.
So John, I think there's a share audio option when you share the screen. Hey, John? Hey, John? Hey, John? John?
So Daniel, if you want to try sharing, you have host permission, so go for it. I have no clue why it didn't share.
So welcome to our tutorial on data real-time analytics theory and
That
practice.
worked.
I'm Daniel Ting, and with me is John Malkin. To let you know a little bit about ourselves and the perspectives that we're coming from, I come from a background in statistics and machine learning. I was initially inspired to work on data sketching. Problems appeared over and over again. And data sketching was one of these ways to deal with some of these problems. Tableau research to spend more time on developing sketching algorithms and theory.
Machine learning. After I was tasked with improving the process by which Yahoo, now a part of Verizon Media, counted unique visitors, when I met Rhodes, who had recently sketches to improve the scalability of metrics calculations. Since then, I've moved to working directly with Lee as a contributor to Apache Data Sketches. Lee, the founder of what is now the Apache Data Sketches project, also contributed to this talk.
And our hope is that regardless of whether or not you're interested in applications and building systems or in algorithms and theory, you'll learn something useful, or at the least something very cool from this.
So for this portion of the tutorial, I'll be talking mostly about some theoretical and algorithmic aspects of data sketching. But before we get to the contents, I'd first like to thank a number of researchers and collaborators who I've had the pleasure of working with or learning from over the years. And in particular, some of these researchers have done some foundational work in data sketches, which researchers like myself are now able to build off of. So why might you consider data sketching? The main problem that data sketching tries to solve is this problem of big data. And as you know, there's a tremendous amount of data being collected and stored in the world right now, and it continues to grow. And although systems have now been engineered that are capable of ingesting, storing, and running massive queries on big data, these systems are also being subject to increased demands due to the number of analyses increasing, and more analysts using these systems, and the more pipelines that are built off of them. And this results in problems in providing scalability and speed at affordable costs. And engineering-based solutions to this problem always hit a fundamental roadblock, namely that in order to execute these queries over big data, you simply need to spend a lot of time reading big data. So data sketching is a way to attack this fundamental problem by making big data into small data. And this opens up some intriguing questions. For example, what possibilities might be opened up if speed and cost are no longer worries? Would you now be able to provide real-time analytics? Would you be able to build new user interfaces or perform automated analyses that previously would have hammered your system, but now can be run comfortably? And in general, what problems would you potentially tackle that you might not have tried before? To define data sketches, I'll give a very general definition. A data sketch can be considered any sort of lossy compression or summarization of data. And all that's required is that this summarization is able to provide answers to some set of questions of interest. The advantages of using data sketching can be quite significant, providing benefits in both space usage and in processing speed. For space, it can reduce the space usage by orders of magnitude, multiple orders of magnitude. And for speed, typically these sketches can be built in one pass and in a parallelizable fashion, and when it comes to query time, it's usually nearly instantaneous to read from them. At the same time, these sketches are not a panacea. There is no free lunch. In order to achieve these space savings, the information that the sketch stores necessarily reduces the amount of information in the full data. And because of this, the sketches can only answer a particular subset of questions or queries, and these queries must often be determined in advance. At the same time, the lossy compression necessitates approximation error in many of these sketches, though often this comes with a theoretical bound. To get a sense of the advantages and limitations of sketches, we can first look at some basic examples that everybody should be familiar with. One example is a simple random sample. Almost any question that could be posed on the original dataset could also be posed on the simple random sample, and the answer simply has some approximation as error associated with it. Another example is histograms. Histograms provide an excellent example of the types of trade-offs that could be made with sketches. It produces a very small summary of the data, which can answer a wide range of questions about a univariate distribution. For example, it can be used to compute the mean, the median, identify if there are outliers or heavy tails, or identify possible modes. At the same time, if you had a question which involved multiple dimensions, the histogram would essentially be useless for that type of question. Other examples include pre-computed aggregates or parametric statistical models. And in this case, the statistical model encodes information about the distribution of the data without providing any specific data points. And while the previous set of sketches are typically used in very common analytic tasks, sketches can also be used in more complex data processing. In particular, there's a set of sketches useful for numerical linear algebra tasks, including those using random projections, sketch singular value decomposition, or in more advanced sampling techniques for accelerating regression. Other advanced methods include Nystrom approximations for coming up with low-ranks approximations to kernel matrices, various methods for constructing core sets that accelerate statistical or machine learning model fitting, and sketches for complex tasks such as for graph problems. To get a sense of the ways that sketches are used, here are a few applications of data sketches. These applications span a variety of disciplines ranging from computer networking to biology. In some applications, like those in network security or in genomic applications, data sketches enable analyses at scales that simply would not be possible or would be cost prohibitive if exact methods were used. For example, to detect a distributed denial of service attack, an exact method may require storing millions or billions of counters for every IP or pairs of IPs. A data sketch, on the other hand, may solve it using a frequent item sketch and or a distinct counting sketch in much less space. Other tasks, such as those in, say, databases or web applications, can involve much smaller data sizes. But in this case, data sketches are used to accelerate frequent operations or reduce the communication cost. For example, in databases, you may issue a query for a particular key or particular item, and a sketch can be used, approximate set membership sketch can be used to determine what files you actually need to read or what can be skipped. And if the key is very unique, then most of the data that you would have read before would be able to be skipped and the query would be vastly accelerated. So for the rest of this talk, I'll be describing several sketches one by one. Most of these will focus on these sketches used for analytic tasks, but I'll touch a little bit upon the more advanced methods. We'll also touch a little bit about the relationship between differential privacy and sketches, and as we go through each of these, I'll highlight key techniques and takeaways as we go through them. So whether or not you're a researcher or a practitioner, our hope is that you'd be able to get something out of this tutorial. For practitioners, this may mean being able to better navigate the world of data sketches. So you may be able to better understand the capabilities of various sketches, or to better understand the types of guarantees that these sketches provide. This may help you also in choosing a sketch to implement. For researchers, given my background in statistics, I'll present a more statistical approach to sketching. And this will sort of impact how you see how sketches are constructed, as well as how you get estimates out of these sketches. I'll also talk a little bit about relatively new developments in the world of data sketching, as well as perhaps some open problems. So this brings us to the first class of data sketches we'll consider, those for approximate distinct counting. And these sketches are now pretty ubiquitous in databases, with some databases even offering press releases when they add this sort of functionality to their offerings. So in this approximate distinct counting or cardinality estimation problem, you're given a data stream or multi-set where the items in the stream can be duplicated multiple times. and your goal is to compute the cardinality, or the number of unique items in this stream. As for this sketch and for every other sketch, the paradigm is essentially that I'm going to take this data stream X, try to process it in a streaming fashion to produce a sketch S, and this sketch can be stored, and I can recover an estimate for the cardinality, or whatever quantity of interest is, later by computing some function n hat of this sketch. To make this problem more concrete, we'll look at one of the most important applications of these distinct counting sketches, namely applications in online advertising. So if you're an advertiser, typically one of the things that you want to know is if I run an ad campaign, how many users do I actually reach? How many eyeballs actually see my ad? And this is because metrics which are additive, like total number of impressions, don't distinguish between a user which saw 100 and same ad 100 times versus 100 distinct users who saw the ad once. And obviously, due to diminishing returns, it's simply not as valuable to have a user that saw an ad 100 times. A second problem that advertisers face is the problem of estimating audience size. If an advertiser is already publishing ads with CNN and The Guardian, then they may ask, should I spend my additional ad budget on the Washington Post, another news site, or maybe a basket of blogging sites would yield a more diverse set of users. Furthermore, you typically also want to know something about the demographic breakdown of the audience that you're reaching. So if you're an ad placement provider, you need to be able to provide the advertisers using your service these metrics which they care about, these metrics about reach and audience size. And so if we look at the reach problem, we can see how to translate this into a database query and how it's executed to see how costly it is to perform an exact computation. So this problem of how many distinct users saw an ad can be translated to a simple database query which says select count distinct user from some very large stream. And to compute this exactly, the naive way to do this would be to take each user, insert it into a hash table, and after all the users have been encountered, you simply count the number of keys in this table. If you had 1 million users who saw an ad, and each user took up 64 bits, then a reasonable estimate of the hash table size would be about 16 megabytes per ad. But these ad placement services aren't dealing with just one ad. They may be dealing with 100,000 ads per day. And so 16 megabytes quickly blows up to 1.6 terabytes per day. And if you also need to provide historical information, this quickly grows to 50 terabytes per month. And if you wanted to add demographic breakdowns, this cost would increase exponentially. So we can look at what happens to the cost when we replace these hash tables with a sketch. So if I were to take these 16 megabyte hash tables and replace them with the hyperlog sketch with 4-bit counters, then my 16 megabyte hash table would suddenly become, say, 2 kilobytes in size. And these sketches would still be able to provide answers with relative error of 1.5%, meaning that if the answer was 1 million before, the new answer, or the estimated cardinality, would be roughly 1 million plus or minus 15,000. And this represents an 8,000 times improvement in space, so that before, where we faced storing 50 terabytes for every month, we can now only store 6 gigabytes, which is quite reasonable to store on just a single machine. So how do these sketches work? Well, in this particular case, the main challenge in building a sketch which works is how to handle duplicates. And that brings us to our first technique in sketching, namely hash-based or coordinated sampling. So hash-based sampling assumes that there exists a universal hash function mapping data items into IID uniform random variables. And as long as I have enough bits in my hash function, then I can be pretty confident that after hashing, I still have n distinct values or very close to it. But the purpose of this hashing is actually to take this data, which came from some unknown domain, and map it into a distribution that I know, and which only depends on this desired cardinality n, thus preserving the information that I care about. Now, simply hashing doesn't solve this problem of needing to store n distinct values. However, since the distribution is now known, I can compute some sort of summary statistic and then use that to try to infer what the original parameter n is. And so the summary statistic, which is stored by one of the commonly used sketches, min count, or also known as the k minimum value sketch, is to simply keep the smallest k distinct values. And this sort of illustrates the general paradigm that you use when you think about data sketching as a statistical problem. First, I'm going to take data, and I'm going to convert it into this random process with some known distribution. And I'm going to construct it in a way where the parameters of this distribution are exactly the answers to my questions of interest. I'm going to build this random process in a way so that it can be updated and stored efficiently. And once I have this sketch, now I simply need to apply the statistical tools at my disposal to perform a parameter estimation problem to actually extract these answers to the queries of interest. So to better understand the min count sketch and how you can obtain a cardinality estimate from it, we can look at an analogous physical process. So imagine there was a beach full of trash, and you wanted to count the total amount of trash on the beach. An easy way to try to estimate this would be to simply take a bag, start at the beginning of the beach, wait until you've collected k items, or until the bag is full, and thus estimate the rate of trash, the rate at which trash appears on the beach. And you just take this rate and multiply it times the length of the beach to find an estimate of the total amount of trash. And min count really follows this process almost perfectly. You take data items, you hash them uniformly into the unit interval, or equivalently uniformly along the beach, and this allows you to take the smallest k items, which are exactly the same as taking the first k items you see on the beach, and this allows you to estimate a rate at which items appear on the unit interval, or the rate at which items appear on the beach. And thus you can get a cardinality estimate. So more formally, the min count sketch stores these k smallest values, z1, z2, up to zk, and it returns a very slightly different estimate. So it returns this estimate k minus 1 divided by zk, the location of the kth item. And what you can figure out with this estimator is that since I know the exact distribution of the zk's, I can actually find the exact distribution of this estimate. I can show that the estimate is unbiased. I can show that the standard error for this estimate is approximately n over square root of k minus 1, so that if I set k to be equal to 102, I know that I'll get approximately 10% error overall. Furthermore, I can actually show that this is the best possible unbiased estimator, namely that it's the minimum variance unbiased estimator using statistical techniques. And compared to other distinct counting sketches, this min count sketch has a number of advantages and disadvantages. All of these stem from the sketch essentially being a random sample. The advantages of the sketch are that it's very flexible. It supports all set operations, including unions, intersections, set difference. You can even apply filtering to the sketch if you have some information about the hashed IDs. The disadvantages, however, are that this flexibility comes at a cost. The sketch can be much larger than other distinct counting sketches. They can be, for example, up to 15 times larger when you're dealing with large cardinalities, and you can have slightly worst case updates. And this idea is also of sampling is also the basis for the theta sketch and tuple sketches, which are also in the Apache Data Sketches library. The advantages and disadvantages of min count speak to an inherent trade-off that's present in data sketches, namely that of flexibility versus efficiency. Since sketches use less space, it necessarily means that they've reduced the amount of information that's contained in them. And because of this, you can't necessarily answer all questions that you could have with original data, but you can only answer a subset of questions. And sketches must pick and choose what queries that it can or cannot answer. And this isn't necessarily a bad thing. For instance, most queries are probably not very interesting or rather useless. you might ask the data, perhaps, how many people queried for Apache data sketches, and also the phrase recipes for banana cream pie. While there is some answer that's present in, say, Google search logs, this question is not one which is of any interest to almost anyone. And so if you imagine there are so many of these sort of pointless questions, we can discard the answers to all of these and restrict ourselves to a set of questions or queries which are potentially interesting. And out of these potentially interesting questions, the sketch may even be able to further reduce the amount of information by only answering the ones where you actually have an interesting answer. So going back to this problem of distinct counting, we can look at the min-count sketch and see how we can trade off flexibility for efficiency. And we can do this through this technique of quantization. When constructing the min-count sketch, we essentially thought of the construction as being a two-stage process. First, you take data and then convert it to a random process, where the parameters of the random process encode the cardinality. Once you have this sketch representing this random process, you perform another stage which estimates the cardinality out of the sketch. What we'll look at now is another stage where we take this random process and then we look for a way to encode it efficiently so that it can be stored in smaller space and allow for fast access. So hyperlog is perhaps the most popular distinct counting sketch out there. And hyperlog improves upon the efficiency of min-count while trading away some of the flexibility. And it does so by making two modifications. First, rather than storing the k smallest hash values, it instead hashes each item into one of k bins and then just stores the smallest value in that bin. And what this does is that it improves the worst case update time, whereas before, if you used a heap to store the k smallest hash values, this may have required log k time in the worst case. Just simply hashing to one of k bins and taking them in is an O of 1 operation. More importantly, the values that are in these bins are quantized. And by doing so, you don't need to store, say, a full floating point number, but you can store a very, very small integer representing that. And by doing so, you can gain substantial space efficiency. To better understand the hyperlog sketch, we'll examine the effects of each of these modifications separately. First, we'll only look at the effects of the binning trick. And in this case, this continuous version of hyperlog, the sketch is represented as a vector in Rk. And the main difference is that when I hash an item, I'm going to assign it to a bin in addition to hashing it to some random uniform value. And the value in the sketch will just be the minimum zi value assigned to a particular bin. And when I want to estimate a cardinality from this sketch, I can use the exact same principles that I used to derive the min-count estimator for this continuous hyperlog estimator. Rather than look at the distance traveled until I see the kth smallest item, I can look at the distance traveled until I see the first item and average over the k replicates that I have. This gives me a rate at which I will encounter items in each of the bins, which I then just multiply times k to get the overall cardinality. And the nice thing about this estimator is that, like the min-count sketch, I can show that this continuous hyperlog estimator is essentially optimal. More precisely, if my cardinality was some number which was Poisson distributed with parameter n, then this continuous hyperlog estimator will essentially correspond to the maximum likelihood estimator for this parameter n. And as you might be familiar with, the maximum likelihood estimator is asymptotically efficient and so effectively optimal. Now if I add some quantization, this continuous hyperlog sketch becomes the actual hyperlog sketch. And for this quantization procedure, the only thing that changes is that where previously I might have stored uniform 0, 1 random variables, I instead take these uniform random variables and transform them by putting them on a log scale and then rounding by taking the ceiling. And what you'll note is that by performing this quantization procedure in the middle, because taking the minimum of quantized values is the same as quantizing after taking the minimum of a bunch of values, I can reconstruct this hyperlog-log sketch by first running this continuous version of the hyperlog-log sketch and then performing the quantization procedure afterwards. So in this sense, it's generating the exact same random process as continuous hyperlog-log, but this doing a further efficient encoding of the information in there. And this, of course, also changes the estimator that I get out, but you can still use the continuous hyperlog-log estimator as sort of a base for it. And basically, all I need to do is undo this quantization procedure in some way. And this can be done by essentially taking the sketch values and then rescaling them back to being between 0 and 1. And that gives me an approximate rate, giving me a decent estimator of the cardinality. However, this estimate is biased. And so to correct for that, I multiply this rate by this term alpha to correct for this quantization. And so for people who are familiar with the hyperlog-log sketch and have seen the formula for it, it initially seems very mysterious, but this sort of gives you a nice clean explanation about why this particular estimator has the form that it has. By comparing hyperlog-log and min-count, we can see what kinds of efficiency gains that hyperlog-log achieves by using this quantization. So for min-count and hyperlog-log, for both of them, we have good estimates of the error, at least for large cardinalities. For min-count, the error is approximately n divided by square root of k, whereas for hyperlog-log, it's 1.04 times n divided by square root of k. And this is rather amazing because if I were to look at the continuous version of hyperlog-log, I would get the exact same error as for min-count. And so hyperlog-log, after this discretization, performs very nearly optimally. It only pays this factor of 1.04, despite throwing away information through this quantization procedure. However, it's able to dramatically reduce the size, whereas min-count used, say, 32 or 64-bit hashes and required k times 64 bits. Hyperlog-log is able to use counters which only use 4 to 6 bits. This gives savings of up to 15 times. However, min-count is able to support more operations, more set operations, including intersections, set difference, and filtering. And so this is the trade-off. You lose the ability to answer a few questions with min-count, but you get a pretty substantial gain in efficiency. So after seeing these two sketches, a natural question to ask is whether or not one of these two sketches could be considered quote-unquote the best. And what you'll find is that when you look at the sketching literature, the answer isn't so obvious. To illustrate this, here's a partial list of distinct counting sketches. You'll notice that there are quite a few, but the question is, which one of these should you pick? And I'll give you a little bit of time to look through these sketches and pick one that you think would be promising. So you might pick this optimal distinct counting sketch as your sketch of choice. But it turns out this quote-unquote optimal algorithm is highly inefficient even though it has optimal space complexity. And this speaks to a disconnect between theoretical results and practice. Whereas theoretical results often quote a rate, in practice the constant factors associated with the rates are often quite important. And it's actually the case that no one sketch dominates the others in all cases. For example, if you have a rough estimate of the cardinality, the linear probabilistic counting sketch would actually do much better than hyperlog-log or the sampling-based sketches. Or if you're in a purely streaming scenario, then the self-learning bitmap can be more efficient than hyperlog-log as well. Or if you only care about the amount of storage space that a sketch the sketch uses, then a compressed version of probabilistic counting would be better than a compressed version of hyperlog-log. However, hyperlog-log and these sampling-based sketches are simply particularly well-rounded sketches, being able to cover basically all scenarios pretty well. But even if you were to settle on just implementing hyperlog-log, in order to get a state-of-the-art implementation, you would need to make a number of improvements over the original algorithm by Flageolet et al. In 2007. For example, you might need to implement the sparse representation for low cardinalities from hyperlog-log plus in Hoyle et al. 2013. And rather than the 5-bit bins in the original algorithm, you might choose to use 4-bit bins using an offset idea from the implementations in Presto, Druid, and data sketches. You might also replace the estimator for cardinalities using an improved raw estimator from Otmar Erdl in 2017. And if you want tight error estimates, you might use the error estimator from one of my own papers in 2019. You might also compress the sketches using ideas from Shoreman and Mauve and Lang 2017. And in the case where you have the data coming as a single stream, the streaming historical inverse probability estimator would give more accurate results. And you can also get a tight error estimate from this from my work in 2014, and Edith's works in 2014 as well. And these are reasons why, even though an algorithm may be seemingly easy to implement, you may want to consider a well-tested library, which has both great engineers working on it, as well as researchers who are actively involved in its development. There are also cases where improvements to HLL have been proposed, but they may not be sensible for you to use in your use case. For example, HLL Telcop Plus does gain some efficiency in smaller space, but it does so by sacrificing the ability to do unions. Losing the ability to do unions is particularly problematic because it destroys a key property of practical sketches, namely that of mergeability. To define mergeability, consider a sketch construction algorithm S that yields estimates where the estimates have error of scale sigma. S is mergeable if there exists a function which will take two sketches, S of D1 and S of D2, both which provide estimates which have errors of scale sigma, and this function generates a new sketch S prime, whose estimate also has error of scale sigma as well. Mergeability is a really important property because it enables distributed processing. For example, if my data was incoming to multiple servers, then I'd be able to sketch the streams at each server and then merge them together, thus eliminating a bottleneck in my processing. Likewise, if I have a huge data set, I may map them out to multiple compute nodes to compute the sketches and then merge them together in a final sketch. This also helps in reliability. For example, if for some reason several items in a stream were dropped in the middle, you'd be able to go back, process these items, and then add them back into your sketch. This also enables further aggregation. For example, if I were to look at a multi-day time window, say for a week, I'd be able to process sketches day by day, and after the fact, be able to aggregate them over the entire week. So going back to this advertising problem of reach estimation, this changes the question from how many distinct users saw a particular ad to how many distinct users saw an ad broken down by the day they saw it, the user's age, gender, country, and device type. And when you have so many breakdowns, the number of counters needed per ad grows exponentially. So if I have 100,000 ads, this may require 15 billion counters, And with 2 kilobyte sketches, now I'm back in the case where I need 30 terabytes. And although sketches that only support unions require you to break down and assign a counter to the finest granularity, to multiple for every breakdown together, by using intersections, I can simply add them up. So in this case, I only need 142 counters per add, yielding 14.2 million counters versus 15 billion. And so even if my sketch might be 1,000 times larger, I may end up with a comparable size as using, say, an HLL sketch. To get a picture of what space daisies you might have by using either the hyperlog or min-count sketch, we can look at this sort of pictorial diagram. On the left, we have the case where you compute cardinalities exactly. We have many, many counters, and for each counter, I need to store a hash table, which requires a significant amount of space. If I were to use a hyperlog sketch, the number of counters stay the same, but I can use far less space per counter. On the other hand, if I used a more flexible sketch, such as the theta sketch or the min-count sketch, I can dramatically reduce the number of counters and only pay, say, a modest price in the space usage per counter. And then the question is simply, which one becomes more beneficial in your particular case? And you might say that, well, if I support unions, in some sense, I can also support intersections through the inclusion-exclusion rule. And this is true. You can compute an estimate for the intersection using this rule. The problem is that these estimates are often terrible. The error tends to be proportional to the largest estimate, namely the estimate for the union. And so if you have two sets with a relatively small intersection, so if they have a Jacquard similarity of 0.1, and if, say, each sketch had estimates that have an error of 2%, then the estimated intersection you would expect to have error of approximately 20% of the intersection value. And this becomes even worse when you're taking multiple intersections. And this brings us back to the usefulness of sampling-based sketches. Like I've mentioned before, these sampling-based sketches tend to be significantly larger than hyperlog if I just want to estimate a single distinct count. But they're often much better at estimating intersections. Furthermore, when you compose these sketches, you can continue to take more and more intersections together, and the output is simply another sketch. So they have this added advantage that they're sort of closed under these set operations, and you can store the result of them by itself. And examples of these sketches include the min-count sketch, also known as the bottom K or K-minimum value sketch, as well as the theta and tuple sketches, which are implemented in Apache data sketches. However, using sketches that support intersections is not the only solution to this problem of computing many distinct aggregates for many, many sets. For example, using a sparse representation for low cardinalities may be sufficient for your problem. In this case, if you have many counters which have low cardinality, you're able to allocate less than, say, 2 kilobytes of space per counter. For these low cardinality sets, the counters only require space proportional to their cardinality. Another idea is this idea of counter sharing. In this case, rather than have each counter occupy its own space in memory, you have the counters share space in some fashion. And in this case, you're still able to answer cardinality questions for sets which have high cardinality accurately. However, sets which have low cardinality may not get a very accurate answer. And thus you sort of prioritize the estimation of sketches or sets which have high cardinality relative to others. So the second sketch that we'll look at is sketches involving sampling. And as alluded to before, the advantages of sampling are that when you use sampling, these samples are extremely flexible. Any question, or rather almost any question that could be answered using the original data could also be answered using the sample. Furthermore, samples are extremely easy to work with. Oftentimes, it requires no changes to downstream methods except to add a sort of weight associated with each item. The disadvantages, of course, are that in order to get this flexibility, these sketches require more space than specialized sketches. And so we'll just cover this sampling very briefly, since other tutorials have also covered sampling. The canonical problem that sampling deals with is a problem called the subset sum problem. For example, it might answer, what are the total sales that have had a promotional discount for items with a promotional discount? Or what are the total sales by product category? In each case, I'm dividing up a sum which might have been total sales into different subcategories, namely items with promotional discount or by product category. And more formally, this just means I want to compute some sum where the sum is over indices from a particular set. And despite this simple form of this subset sum problem, it can actually answer many, many questions. For example, you can recast distinct counting as a sum. You can recast intersections as subset sums. And in some cases, you can convert parametric statistical or machine learning models into something which is asymptotically a sum. And the problem is really just, how do you do better than simple uniform sampling? To do this, we first provide an unbiased estimator for the subset sum that works for any sampling procedure. This estimator is the Horvath-Thompson estimator. We can then look at how to construct a sketch or sampling procedure that minimizes the variance of this estimator. The Horvath-Thompson estimator is a way to estimate sums for samples drawn without replacement. In this case, the items themselves are not random. Only whether or not an item is included is random. If we denote the inclusion of this ith item by zi, and the probability of inclusion by pi, then the Horvath-Thompson estimator is the sum over items in the sample reweighted by the inverse of the inclusion probability. And it's easy to see that this is an unbiased estimate, since the expected weight for each item is 1. So the problem now is to figure out what inclusion probabilities will minimize the variance of the Horvath-Thompson estimator. And the technique we'll turn to now is probability proportional to size, or PPS sampling. So a probability proportional to size sample chooses item inclusion probabilities that are proportional to the magnitude of the items themselves. And these probabilities can then be rescaled so the sample has an expected size equal to a desired sample size k0. And what's key to note here is that larger items which contribute more to the sum are also be included. More specifically, any non-zero contribution to the Horvath-Thompson estimator will have a constant value. And what this means is that there's no variability coming from the values of the sum, only from the number of values. More formally, if we look at the breakdown of a variance into the conditional variance and conditional expectation, then we see that it can eliminate one term in this breakdown. However, there are some challenges in applying these techniques in streaming settings. In probability proportional to size sampling, the inclusion probabilities need to be set in advance. And these inclusion probabilities depend on data X, which is unknown in advance in streaming settings. Furthermore, if you want to keep the sketch size or sample size fixed, then the inclusion probabilities need to continually decrease as you see more and more items. And in this case, where you do have bounded sample sizes, items also can't be drawn independently. One item's inclusion necessarily kicks out another item. And in this case, the true inclusion probabilities are actually intractable to compute. So what sketches for sampling do is that they provide ways to draw PPS-like samples without replacement in bounded space. And they get around this problem of intractability by replacing the true inclusion probabilities with some sort of easier to compute pseudo-inclusion probabilities. And algorithms that do this include priority sampling and var-op sampling. They also provide ways to extend these basic techniques. For example, if you had multi-dimensional items, you might use multi-objective sampling, which allows you to do well regardless of whether or not you're computing a sum over the first dimension or second dimension or any other dimension. So one last thing I'd like to do is to contrast Horvath-Thompson estimation and PPS sampling with another commonly used technique, importance sampling, and to describe a little bit about when each is appropriate to use. So importance sampling is a way to estimate sums using samples that are drawn with replacement. And in many ways, it looks exactly like Horvath-Thompson estimation with PPS sampling. In both cases, you draw the ith point with probability proportional to the magnitude of that item. Except in importance sampling, you do so with replacement, and you choose inclusion probabilities so that they're rescaled to sum to 1, rather than to maintain some sort of expected sample size. And the disadvantage of importance sampling is that you can potentially have many duplicated items in your sample. So in this example, we have an item E whose weight is equal to half of the total weight in the data. And importance sampling in this case will waste half of the sample just repeatedly sampling the same value. And so if I have a subset sum query which doesn't include this item, my effective sample size is now half of what it could have been. Furthermore, if I have a query that includes E, now the contribution of E is random rather than fixed and exact. So both of these techniques still have their use cases. For Horvath-Thompson and probability proportional size sampling, these techniques are good when you have a fixed data set or some sort of discrete distribution. On the other hand, importance sampling is still useful when you're doing Monte Carlo estimation with a continuous distribution, and also in cases where, in theory, you need to prove something, and the dependence in the importance sampling technique makes the proof easier. Though in this case, if your distribution is discrete or you have a fixed data set, in practice you would still just substitute in and use Horvath-Thompson estimation with probability proportional to size sampling. So now we'll just take a quick break before we move on to the next topic of quantile sketches.
Sorry everyone about these technical issues. If you have any questions, we can take any that you might have at this time. And we'll restart at 2:20.
I'm gonna attempt to share the video for the next part and see if I can get audio to play. I don't know if it'll work. Company policy, I'm not supposed to install the Zoom app on this laptop. So if the web browser doesn't let me do it, I'm unable to do that. So we're not going to start quite yet, but I am going to experiment briefly. Did audio come through on that?
No.
I have no clue why. I hear it locally. So my only conclusion is that it's got to be something with not being able to do the with the app. Odd. We can probably read out the questions and answer orally as well.
Oh yeah, that's probably a good idea.
Okay, so just had a question: Is mergeability and are mergeability and aggregation the same? if there are two count min sketches with the same hash function and buckets, can we simply add them to merge them to a master sketch? So got to be a little bit careful with terminology here. You can take the two sketches and you can merge them, and that will be able to produce another sketch with the estimate of the combination. So yes.
So the main difference is that the sketching literature mergeability is more specific in the sense that if you merge two sketches, they should have the same error guarantees in some sense. So like if you're thinking about intersections, that type of stuff, then that'd be some kind of aggregation, but not be exactly mergeable in the same sense, right? So if you take intersections of these distinct counting sketches, your error gets worse. So that's kind of the main difference between the terms. But yeah, typically if you care about aggregation, you also care about mergeability.
So I'll touch on it in the practical sketching portion, but one of the things that mergeability gives you is that you can treat things as additive in practice because merging is typically fast. But it is important to make sure you're keeping terminology straight, since sometimes people will think you can just take the sketch estimates and add them, and that does not work properly.
Other class of sketches that we consider are quantile sketches.
Okay, next question. Once all the sketches are covered, can we please elaborate which are best to use in which scenarios, as in trade-offs between choices for people who are unfamiliar with these? Yeah, we can talk over them briefly.
Yeah, I think we're asking some questions about your particular scenario.
But yeah, it's really hard to have a completely generic answer to that. So throwing out some types of scenarios ends up being easier.
Right, a lot of them, it's the sketches fall into specific categories, right? They answer specific questions. So distinct counting sketches are particularly good for distinct counting, and then some set operations. Some, if you would care about like set similarity, like Jacquard indices and things like that, then like they're basically, they could be used for distinct counting, but there are some sketches which are more suited for that purpose. There's quantile sketches, right? Sort of the best, we'll talk about this very in the next section, but there's kind of one sketch which tends to be good in all scenarios. It has good theoretical performance. Times, if you care about tails, just white tails, and so maybe a sketch which doesn't provide the theoretical guarantees might be more suitable for your purpose. So some things there's right, some gaps in the theory and practice as well, which makes it a little bit harder to say, to nail down one specific sketch which is great for your purpose. Did we read out the question? Yes.
Okay, about 2 minutes.
In general, we'd also like to hear more about your scenarios. There may be gaps, or there probably are gaps that the theory just doesn't answer some questions. It may not be possible to, but it may also just be that people haven't thought about the problem. And so we'd love to hear more about what problems you face that you hope that sketches solve.
And of course, there's also, there are certainly sketches that exist in theory, but where there isn't necessarily a good implementation ready for use, especially not if you work at like a company or are doing anything super critical. One important part of a lot of sketching libraries is testing. And certainly when building the Apache library, we've been testing our own and we've tested against other implementations. And we have definitely found significant bugs in other common implementations. We've also found bugs in ours, but we can fix those ourselves. So we don't know of any bugs in any major bugs in our current releases, but this is, yeah, all software has them somewhere. But yeah, aggressive testing is important when you're dealing with probabilistic algorithms, since it's hard to just reason through them, and especially if they're truly random, you can fix your random seed, but that actually makes it harder to ensure that you didn't just get a lucky sample.
Yeah, so we'll go ahead and start the second part on the original videos, and hopefully this will be a little bit smoother. Yeah, fingers crossed.
Measure the worst case behavior that a user might. The third class of sketches that we'll consider are quantile sketches. Sketches are commonly used in computing metrics. For example, they're commonly used in computing quality of service metrics, which measure the worst case behavior that a user might typically encounter. For example, it may be used to measure the 99th percentile latency for page load times, or for battery life, or other measures which you want to have a large or a particularly small number for. They can also be used to compute robust metrics such as the median, or if you are interested in the spread in the interquartile range. And another common use case is in setting anomaly detection thresholds. For example, if you want to be alerted when you have a value which is above the 99.9th percentile because you decided that that's a large value which is large enough to be worth investigating, then you need to be able to compute these thresholds very accurately. And quantile sketches are particularly useful in some ways, in the sense that not only do they save space, but as you're computing them, they save a very expensive operation. So if you were to compute a quantile exactly, a very simple approach would be to sort a large array and a slightly better approach would be to run a sort of quick select algorithm. Either way, you need to store this large array and perform quite an expensive operation on it. But when you use Quantile sketches, you're able to remove this expensive operation and replace it with many small sorting operations or something cheaper. Furthermore, these Quantile sketches are extremely accurate. If you have a desired error epsilon, the space usage is typically on the order of O of 1 over epsilon versus O of 1 over epsilon squared for sampling-based approaches. And this is useful in, say, an A/B test. In this case, if you're interested in the 90th percent quantile and you had 10 million data points, then in order to get a confidence interval or a hypothesis test where the accuracy of your sketch is much smaller than the natural sampling variability, then you need to be able to accurately compute the 90.02 percentiles and the 89.98% quantiles. And this implies an error, desired error of roughly 0.0001. And if I were to use a sampling-based approach, then I would basically need to store as many points as I originally had. Whereas with a quantile sketch, I'm able to significantly reduce it to a number of samples, which is roughly 10 to the k, or 10k, or about 1,000 times less than originally. And in practice, quantile sketches are quite intriguing in the sense that many systems have chosen different quantile sketches to implement. And that's very different from the case of distinct counting, where almost every system has coalesced on using either HLL or min count. For example, Spark chose to implement the Greenwald-Kana algorithm, while Presto uses the Q-digest. Several systems such as Splunk or Dynatrace use the T-digest, whereas Apache Data Sketches chose to use the KLL or the Karnan-Liberty-Lang sketch. Other companies use DD sketch, and other systems have implemented another sketch called the moment sketch. And it's not simply the case that all of these sketches have their advantages and disadvantages, and systems are making these choices based off of some trade-offs that they want to make, but it's actually the case that major real-world databases are simply making suboptimal choices. For example, Presto uses the Q-digest, and a past empirical comparison of these sketches shows that the Q-digest is an order of magnitude worse, both in space and in update time. And this speaks to some of the challenges that you face when navigating quantile sketches. In particular, for quantile sketches, you typically don't have. So to help navigate quantile sketches, we can break them down into roughly 3 categories based on the techniques used and the guarantees they provide. First is the class of comparison-based sketches. These include the Greenwald-Kana sketch, the KLL sketch, the Mangu Rajagopal-Lindsay sketch, and the relative error streaming quantile sketch. And all of these sketches provide what I would call strong error guarantees. The second class of sketches assume that the domain of values come from some fixed universe which you know ahead of time. In this case, you have the Q-digest and the dyadic count sketch, and these also provide strong error guarantees, but in practice they often have somewhat worse space usage. The dyadic count sketch also has the advantage of being able to handle deletions from the stream. And the third class is the class of heuristic sketches, or sketches with distributional assumptions. And these include the popular T-digest, the DD sketch, as well as the moment sketch. And in this case, all of these sketches provide weak to no guarantees, and sometimes these guarantees require some strong assumptions on the distribution of the data. However, at times they can still work pretty well in practice. So let's look at the error guarantees that these sketches provide. So for the quantile problem, you're interested in essentially 2 quantities. first is the cumulative distribution function f, and the second is the Q quantile, which is defined to basically be the inverse of the cumulative distribution function at Q. And all of these quantile sketches essentially provide a guarantee on this cumulative distribution function. In a neighborhood of the quantile which I actually care about, the CDF is accurate up to some error epsilon. And so if I ask for a Q quantile, the result is that I may get something which is the Q minus epsilon quantile or the Q plus epsilon quantile, but I won't be able to get a guarantee on the raw values. So I won't be able to get an error of the form xq plus or minus epsilon, but I'll be able to say that it's within this interval expressed in other quantiles. And these strong error guarantees have no assumptions on the input streams, so they're valid for worst case inputs. At times, there are probabilistic guarantees that hold with probability 1 minus delta, where delta is a specified acceptable failure probability. However, you're typically also able to get precise error bounds. So you're able to get a upper bound and lower bound on the error, though this error bound may not be extremely tight. In contrast, an example of a weak guarantee is that provided by the DD sketch. So the DD sketch is essentially a histogram where I've taken the values and transformed them to a log scale. And I only care about one side of the distribution, and so what I do is I take all the bins on the side of the histogram that I don't care about and collapse those, and only keep the bins on the side that I care about. And by putting things on a log scale, you get an interesting guarantee. Namely, I'm able to express the error in the estimated quantile in terms of the actual quantile itself. So x hat q is equal to xq times 1 plus or minus epsilon. So it's a multiplicative error guarantee. The problem is that this guarantee requires some distributional assumptions. In particular, the value should come from some bounded interval 0 to c, and the true quantile needs to be within m bins of the maximum value. And this is sort of a circular guarantee in the sense that you choose to store m bins, and you say, I'll provide a guarantee if the value happens to be in one of the m bins I chose to store. Another example of a weak guarantee is that provided by the moment sketch. In this case, there are also some strong distributional assumptions, namely, again, the data is on some bounded interval, and furthermore, you assume that the density of the data is bounded. And you get a guarantee which is, rather than on the raw values of the CDF, you get a guarantee on the norm of the CDF. And so with this bound on the norm, you're not able to say anything about the error for a specific desired quantile. That could be sort of arbitrarily bad, as long as your estimates are good everywhere else. Furthermore, unlike the strong error guarantees, where you can still provide an upper and lower bound for your quantile estimates, this guarantee only provides this rate. There's no error bound for either the CDF itself, the overall CDF itself, or for any particular quantile. So if you're interested in sketches that provide theoretical guarantees where you can trust them in all scenarios, and you also want to have good empirical performance, this tends to lead us to consider these comparison-based sketches. So I've listed four comparison-based sketches here, two variations of the KLL sketch, the MRL sketch, and the Greenwald-Kana sketch. These are two sketches with deterministic guarantees. And so what you see is the optimal sketch, the KLL sketch, which uses the Greenwald-Kana sketch as a subcomponent, is optimal, but by obtaining this optimal randomized space complexity, you end up with a sketch which is not mergeable, or at least there's no space guarantee when you try to merge these sketches. And so a natural choice then is to choose the other variation of the KLL sketch, which is mergeable. And even though you pay some small price in terms of the the theoretical space complexity, this constant factor is actually quite small since it depends on this doubly logarithmic factor. Furthermore, you'll also notice that the probabilistic sketches and deterministic sketches yield quite different space guarantees. In particular, the deterministic sketches have a dependence on the stream length n, whereas the probabilistic ones have no dependence on n. And this yields a pretty big difference in the constant factors, or rather the asymptotic factors for these two classes. Furthermore, you'll see that the Greenwald-Khanna sketch is actually an optimal deterministic comparison-based sketch, meaning that this factor depending on n can't be removed. You'll also notice that with the probabilistic sketches, this dependence on the failure probability delta is very weak. And so even if you can't get a perfectly deterministic guarantee, you can actually set delta to be extremely small, say smaller than the probability that your cluster crashes. And in this case, you get a guarantee which is almost as good as a deterministic guarantee, but you still get good space efficiency. So for these comparison-based randomized sketches, we'll describe just very briefly how they work. So for all of these randomized comparison-based sketches, they work by constructing a compactor, a so-called compactor, which provides a sample which is, in some sense, better than uniform. And then it just simply takes these compactors and stacks them up. And what a compactor does is it simply takes all of the items which are inserted into the compactor, it sorts them, and then it chooses to either randomly select all even indices or all odd indices. And for these selected items, you just double the weight. And so now, if I were to say sort the values between 1 and 100 and ask how many, what's the total weight for items less than x, where x is even, then in this case, the sample that the compactor returns will be able to provide you with an exact answer. By contrast, if I simply took a uniform random sample from this array, then the answer will be random, so it'll be binomially distributed specifically. And so by constructing these compactors, which are better than uniform, and stacking them up, you can get more accurate results and also control the number of compactions so that you can get a type bound, or rather a upper bound on the actual error at any particular point. Now all the sketches we've talked about so far provide a sort of uniform error guarantee, namely that regardless of the quantile I'm interested in, the CDF at that quantile is going to have error of approximately epsilon. But in many cases, I'm only interested in tail quantiles. For example, for quality of service metrics, many of these quantiles of interest are the 99th percentiles, or for anomaly detection, the percentiles may be even higher. And this may explain one of the reasons that heuristic approaches have been popular. Some of these heuristic approaches are able to target tail quantiles, such as the DD sketch and T-digest. And although there actually are existing sketches which are theoretically sound, it turns out that these sketches are not always practical. So for these theoretically sound sketches, they typically provide a guarantee which says that the error is going to be of order epsilon q or epsilon 1 minus q. Whereas for a regular quantile sketch, this error is just going to be epsilon. And if I ask for a 99th percentile, then this means that my error will be epsilon divided by 100 versus epsilon. And so I can set my error parameter to be 100 times larger. You might think that this would result in improved space usage, but the space complexity bounds of these sketches tends to be worse, particularly that of Zhang and Wang in 2007, contains a log cubed epsilon n factor. And the other sketch with with the guarantee is the variation of the Q digest, which we saw before may not have great constant factors associated with it. So what you find is that you often have the case where a KLL sketch, as if you just set a smaller error to it, would actually be smaller for practical values of Q than one of these theoretically motivated sketches. However, some new developments may change that. A very recent work, which is still just in the archives, provides this new relative error streaming quantile sketch, which obtains a much better space complexity and is based off of the same randomized comparison-based base sketch ideas. So in summary, for quantile sketches, even though many systems have chosen to implement different sketches, based on the sketching literature, both theoretical aspects and empirical aspects, it actually turns out that it's fairly clear which sketch could be considered the best sketch, at least in the case where theoretical guarantees are concerned. In this case, the KLL sketch is the best sketch when you want theoretical guarantees, good practical performance, and randomized guarantees are acceptable. However, heuristic approaches are still difficult to compare to these theoretical approaches, and it may still be the case that the T-digest can work really well, or in some cases perhaps the DD sketch as well. However, in more recent developments, it may be also worth considering sketches which are tailored for tail quantiles, in particular this relative error quantile sketch. Another class of data sketches worth considering are the class of top K, also known as frequent item or heavy hitter sketches. And these sketches can be used in applications such as in network monitoring for detecting a DDoS attack, in analytics, for example, for finding the top selling products or the K heaviest users of a service. They can also be used in recommendations to find, say, trending topics. More formally, they solve this problem where if I'm given a stream of key increment pairs, how do we find the keys that have the largest total sums associated with them? So let's look at one particular heavy hitter sketch, namely the space-saving sketch. So the space-saving sketch works by maintaining m different counters, each associated with an item. And if I encounter a new item and that item is already in the sketch, then what I simply do is increment that counter associated with it. However, if I encounter a new item which is not in the sketch, then I'll add the increment to the smallest bin and simply change the bin label. And this simple sketch has some nice properties. If I define a heavy hitter to be any item which appears n over m times, or where the total increment for that item is greater than n over m, where n is the sum over all increments, then this sketch has a deterministic guarantee that every heavy hitter is included in the sketch. And space saving and its equivalent Miser-Grease sketch, along with its variants, are currently the best heavy hitter sketch, both in literature and in practice, at least in the case where you know that there exist heavy hitters and only heavy hitters are of interest. And this provides a good illustration of the difference between being potentially able to answer a query and being able to answer a query accurately. So in this case, the sketch is designed to potentially be able to answer any question for the count of any particular item. However, it's only able to accurately answer that question if that item is a heavy hitter. And while the sketch can be very efficient in answering that particular question, the flexibility of the sketch is quite poor. For example, if there were no heavy hitters in the sketch, then the sketch is actually basically useless. But what you can do is you can look at the sort of reverse process. Instead of taking a flexible sketch and trying to make it more efficient, we can take this efficient sketch and try to make it more flexible. And we can do this with the power of randomization. With just a little bit of randomization, you can extend the functionality and be able to compute subset sums with this now. And this randomization comes in a very tiny modification of the space-saving algorithm. So to get the unbiased space saving algorithm, all you do is when you encounter a new item, which is not in the sketch, you still add it to the smallest bin. However, you only change the label with probability 1 over b, where b is the size of that, or the count associated with that smallest bin. And this sketch has some pretty nice properties. If you're given an IID input data stream, then you essentially lose nothing in terms of its ability to pick out heavy hitters. The heavy hitters are going to be recovered almost surely as the stream grows. Furthermore, the sketch asymptotically generates a PPS sample, where the size is proportional to each item's total count. And you're able to do this without even knowing the item counts a priori. This makes it good for these subset sum aggregation tasks, and it makes it particularly useful for event streams, for example in click streams or in impression streams, where every event has a weight of 1, but you want to sample the ones which have a large number of total clicks or total impressions. And even in this case where the input stream is not IID, you're still able to get a sketch which generates unbiased weights and is able to get unbiased estimates of the count for each item. And this kind of result leads to the following takeaway. Sometimes you should consider more flexible sketches rather than more efficient ones, because it's often more space efficient to choose one sketch that'll solve 2 problems rather than 2 sketches that are the best for their specific problems. So the sketches that we've considered so far for distinct counting, for sampling, for the quantiles problem, and for the top K heavy hitters problem, these sketches are, I'd posit, the most commonly used sketches. What we'll look at now are a class of sketches called linear sketches, which encompasses a sort of more powerful technique that can be used to solve a variety of problems. So a linear sketch is simply a linear transformation of the data. So I imagine my data being some matrix or vector x, and I create this matrix M, which does not depend on x, to generate a sketch S by just multiplying these two things together. And when I do this, such a sketch automatically is mergeable. So if I were to take 2 different data streams and compress them using the same matrix, then I would have that a new sketch is simply the sum of the 2 previous sketches. Likewise, this sketch can also automatically support deletions in the stream by simply subtracting off the compressed version of that deletion. And one way which these linear sketches are used are in terms of general purpose counting sketches. So in this case, I have a data stream of key value pairs, or key increment pairs, and I want to compute, say, sum group by key. So the situation is very similar to this, the frequent item sketch, except now I actually care about every single item, not just the heavy hitters. So it has a similar sorts of situations of which it's useful for. If I'm given an event stream of, say, delivered ad IDs, and I want to compute the total number of impressions per ad, then this sketch is very appropriate for that. It can also be used as a component for other sketches. For example, it's used as a base component for the dyadic count sketch, which is a quantile sketch, and it can be used to compute heavy hitters, though less efficiently. And one particularly useful sketch is, for this counting problem, is the count min sketch. And so what this sketch is it's arranged as a d by w array of counters, where d represents the depth and w represents the width. And whenever I'm given a pair kx from the stream, each key hashes to d counters, 1 in each row, and increments the corresponding counter by x. And so what you see immediately is that this sketch is simply a linear mapping of the total count vector v. I'm just taking things and adding them to fixed positions. A particular index in this vector maps to a particular set of indices in this sketch, and it always just adds up. And this design of this count-min sketch is particularly useful for illustrating a common technique used in data sketches, namely that of success amplification through replication and the resulting concentration inequalities that result from it. So to see how this idea of replication arises in the count-min sketch, you can note that for every key, that key is hashed independently to a random column for every row. And so if I look at the entry for a particular row, I'll see that the entry corresponding to a key is equal to vk, which is the true count or true sum that I'm interested in, plus some error term epsilon I that depends on just random hash collisions. And since this hashing for each row is done independently, all of these error terms epsilon I are independent of each other. Furthermore, when all of the counts or all of the sums that we're computing are positive, or at least non-negative, then each of these vk plus epsilon i's are independent upper bounds, which can be used as an estimate for vk. So count-min does exactly that. It takes these upper bounds, takes the minimum of them to find the tightest bound, and uses that as the estimate for vk. And this easily illustrates this idea of success amplification. If one estimate has a failure probability of being larger than some value c, so the probability of epsilon being greater than c is rho, then if I take the minimum of d estimates, it has exponentially smaller failure probability. And many analyses for sketching are based on these sort of similar probabilistic inequalities, but perhaps more complicated ones, including Markov's inequality, Asimov-Hufting, Bernstein inequalities, etc. And although the idea of success amplification and the corresponding concentration inequalities can be quite helpful in thinking about how to construct a sketch and also improving space complexity bounds, the actual precise bounds that these methods return can often be too wide to be of practical use. And this can have significant implications. For example, if I'm presented two estimators, if the bounds are too wide, I may not be able to choose which estimator is better. Furthermore, when I return an estimate, I may not know exactly how good that estimate or how much I should trust it. And you may ask, what are there ways to get around this where I can get both good estimates and also a good sense of what the actual error is? Fortunately, the answer is yes in many cases, and this can be done by using optimal statistical estimation techniques. And the advantages of using statistical estimation techniques are that these techniques tend to be general techniques that work on a variety of problems. For example, the maximum likelihood estimator can be applied whenever you can derive the likelihood. These techniques also automatically have several good properties. Again, the maximum likelihood is known to be asymptotically efficient, which basically means that it has the minimum variance asymptotically. It's also known to have consistency properties, and you can produce tight error estimates. Furthermore, these methods are useful for analyzing finite sample behavior. The entire field of statistics is basically predicated on this fact that when we analyze the asymptotics and preserve the correct leading constants, we get good approximations to finite sample behavior. When applied to the count-min sketch, we can see that these statistical estimation techniques, when applied to it, can produce error estimates that are an order of magnitude better. What may not be so obvious in this particular plot is that, furthermore, these errors are actually tight, and they also allow us to choose better estimators in some scenarios than the min estimator. So let's look briefly at how this works. So with the count-min sketch, we've looked at the entries which correspond to a particular key. And in these entries, they're associated with some additive error term. But if I look at the entries which don't correspond to a particular key, I also find that they correspond to error terms. And these error terms are identically distributed to the error terms that are in the entries that I care about. And so I can simply use these error terms to estimate an error distribution. And once I have that, I can produce a likelihood and use statistical estimation techniques to yield improved estimates and tight error bounds. And having a tight error bound doesn't just help the end user who can evaluate how reliable a query answer is, it can also help the systems builder who's implementing these sketches. Not only does a systems builder need to choose what sketch to use, but given a choice of sketch, he or she needs to size the sketch and choose the parameters to achieve some sort of desired error for the system. And this can be very time-consuming to do empirically, and in cases especially like those in the count-min sketch, where the error depends on the data itself, they often can't be trusted because the data may be changing. And so it's preferable to use theory, which can return tight error bounds. And these tight error bounds then make it feasible to optimize for the best sketch parameters. So now we'll start looking at some more advanced techniques. First, we'll look at the technique of random projections. And these are essentially just a generalization of the linear sketches that we saw that we used for counting. And so what we do is we take a data matrix X, we're going to multiply it times a random matrix or a random projection matrix M, and produce this sketch S. And really the only question is, how do I produce this matrix M? Ideally, I want M to be some matrix with random entries such that M transpose M is approximately the identity matrix. And when this happens, then if I take a matrix product, I can simply compress the two matrices and multiply their sketches together to obtain an estimate of the original matrix multiplication. And typically what I do is you take these entries to be random Gaussian, independent random Gaussians. And when I use this random projection, I get an amazing result called the Johnson-Lindenstrauss theorem, which states that when I use this Gaussian random projection, it allows me to simultaneously preserve all pairwise distances in my original data matrix. It also implies that inner products are preserved. And the simple condition that's required is that I only need logarithmically many terms with respect to the dimension d for my data points. And this ability to preserve inner point distances and inner products lead to a number of useful applications. For example, it can be used to produce other counting sketches. It can also be heavily used in machine learning models. For example, many of these models depend on inner point Euclidean distances, for example, for clustering problems. You also have cases where inner products are useful. You may have count-based features, which are used in a generalized linear model, for example. And these sketches then allow you to both do this aggregation to produce the counts and also generate these inner products. It can also be used in dimensionality reduction problems and in solving basic numerical linear algebra problems where you can generate a fast iterative solver. We'll now look briefly at some other advanced methods just to get a taste of what's possible with sketches. So one problem for advanced methods is, how do you generate a good sample for a statistical or machine learning model? There are several ways to try to do this, including leverage score sampling, local case control sampling. The one I'll talk about is a technique called influence-based sampling. And this one is, again, based on optimal statistical estimation. It relies on this fact that many estimators are loss minimizers or likelihood maximizers, also called M estimators, and they're often theoretically analyzed as a sum. And by being able to rewrite this thing as a sum of these influence functions, I'm able to bring to bear all of the past mechanisms or machinery for estimating simple subset sums to this problem. And so what you find is that if you can compute the influence function exactly and you use PPS sampling, then you get a sample which is asymptotically optimal. Another set of problems that are interesting are those where you generate a sketch that acts as a matrix approximation. One such sketch is that of frequent directions. And what frequent directions does is it computes a singular value decomposition in a streaming fashion, or at least it computes the top right singular vectors in a stream with the corresponding singular values. And what's particularly interesting about this sketch is that it bears a strong resemblance to the Mies-Righi sketch used for frequent items. And thus it sort of, again, shows this ability to take the ideas which we use for simple sketches or simple problems and bring them to bear in more advanced problems. Another matrix approximation is the Nystrom approximation. And what these do are that they're used for approximating low-rank kernel matrices. And so with kernel matrices, I typically have to compute a giant matrix with n squared entries. And by using a Nystrom approximation, I can reduce this quadratic dependence on the number of data points to something much smaller. And these can be used for approximating Gaussian processes, in general kernel methods, or in spectral graph-based methods. Another interesting technique is that of core sets. And what a core set is any set of weighted points C which can be used in place of the original data X to obtain some sort of accurate approximation. And typically the thing that you want to approximate is some sort of cost function for a model. And this technique is more general than sampling because although core sets can be generated through sampling, they can also be generated through other procedures such as optimization or some geometric arguments. And some examples of where core sets are used include SVMs, Bayesian methods, and in clustering, where we essentially try to accelerate the model fitting by reducing the amount of data that they need to process. In particular, SVMs are a particularly good use case since, by definition, an SVM is only impacted by the support vectors, which is a much smaller subset of the original data. Another area where sketches have been used is in graph problems. And this is because graphs pose some unique challenges since they can grow to be very large very easily, and furthermore, you typically can't pick nodes or edges independently and still preserve the salient features of the graph. For example, sketch has been used to compute minimum spanning trees, maximum weight matchings, and to performing graph sparsification, in which you preserve something called the spectrum of the graph. In each of these cases, you can see that if I randomly pick nodes and edges, you run the risk of disconnecting the graph in some way which is undesirable. So the last topic we'll look at is that of data privacy and its relationship to data sketching. And so data sketches have been used in two ways in terms of data privacy. First, they've been used to identify privacy risks, and secondly, they've been used in the privacy-preserving data collection process itself. To see an example of how data sketches can be used to identify privacy risks, we can look at one such data sketch, namely the k-hyperlog sketch. In this case, you imagine there's a sensitive data set which maybe has user IDs removed, but contains, say, a user agent string or some other potentially privacy compromising string. If you find that the user agent string is associated with a unique ID, then you may find that you can join non-sensitive data that contains this UA string to this sensitive data set. And by doing so, you may violate the privacy of the user who could be identified in this non-sensitive data set. And you can sort of get a sense of the privacy risk by looking at a sort of histogram. This histogram shows the number of unique IDs per user agent. So on the left, we have most user agent strings are associated with a unique user ID. And this constitutes a privacy violation. And the question then is, how do I construct this histogram using a sketch? And the k-hyperlog sketch does this in a very simple manner. So it basically composes a sampling-based method with a distinct counting sketch. So first it uses a k-minimum value sketch to sample a set of user agent strings, and then for each of these user agent strings, you use a hyperlog sketch to estimate the number of distinct users associated with these user agent strings. And by doing so, you immediately are able to produce this histogram, which identifies privacy risks. A second way in which data sketches is related to data privacy is that data sketches can be used in a differentially private data collection mechanism itself. So I'll talk a little bit about the definition of differential privacy, though it won't be critical in understanding how data sketches are related to it. So an algorithm A is epsilon differentially private if for any data sets D1 and D2 differing in only one data point, and for any set S, you have the likelihood of seeing some output from this algorithm when it's given D1, and the likelihood that you see an output given dataset D2, that these likelihoods are very close to each other, that they differ by this term epsilon, e to the epsilon minus 1. So colloquially, what this means is that even if you knew everything about everyone else in the database, and so you differ only in one data point for that single person that you want to snoop on, then you'd only be about epsilon more sure about that person's true value. And so the advantage of differential privacy is that it provides provable privacy guarantees, unlike other criteria such as k-anonymity, which doesn't. So the problems that data sketching tries to solve are closely connected to the problems that differentially private data collection methods are also trying to solve. Namely, they're often computing simple sum aggregations over a large set of keys. And what sketches do is that it's able to substantially reduce the amount of data that needs to be transferred. And this is because differentially private mechanisms rely on injecting noise. So before, if you had a sparse vector of key value pairs, this vector becomes not sparse since I need to add noise to even unobserved keys. So if there are a million websites I wish to monitor, I now have to send a vector of 1,000,000 values. Whereas if I compress this first using a count min sketch, then the number of entries that I need to send becomes much smaller. Furthermore, because every entry needs to have noise added to it, by putting it into a sketch, there are fewer entries to add noise to, and so you can potentially decrease the amount of noise that you're adding into the process. Another advantage of data sketches is that it allows for privatized or changing domains. For example, in this website example, if there's some new website that you want to monitor, you would simply hash it to some additional entries if you used a count sketch. However, if you've represented all websites as unique entries in a vector, then an adversary would know when you add these websites that you're interested in monitoring. And lastly, sketches themselves can introduce some noise-like behavior. In this case, it's not well analyzed how this affects the differential privacy guarantees, since the differentially private definition only allows for a change in one single entry. And in this case, the sketch may not offer some benefit under this strict definition of differential privacy, but perhaps there could be some other scenario in which you can exploit this behavior of adding noise. And another interesting thing about data sketches and privacy is that in both this case of the k-hyperlog sketch and in this other sketch called the private count mean sketch, both of these sketches were developed in industry and used by industry. So Google developed the k-HLL sketch, while Apple developed the private count mean sketch. They also introduced other data sketching techniques into this problem, namely the fast Hadamard transform, in order to further reduce communication costs from sending an entire row in a sketch, which can still be quite large, down to only sending one bit. So that pretty much concludes this part of the tutorial. And we can recap briefly what we've learned today. We've gone over a number of sketches, in particular some of the sketches which are the most commonly used. For example, distinct counting sketches, quantile sketches, frequent item or heavy hitter sketches, and sampling techniques. We've also gone over another important class of sketches, which are linear sketches and random projections. And we've briefly touched upon more advanced sketches and what they're capable of. In most of these cases, we've talked a little bit about how these sketches work. We've gone over techniques for constructing sketches and obtaining estimates from them, and we've done this from a statistical perspective, where we can view a sketch as essentially an efficiently encoded random process. And this allows us to use statistical techniques to improve sketches and to improve estimates and error estimates. We've also looked into some of the principles behind sketches, namely, because sketches reduce the amount of information, they inherently need to trade off in some form or fashion flexibility with efficiency. We've looked at how queries can be viewed as a set of all queries, most of which are uninteresting, to a subset of interesting queries, and to a further subset of queries with interesting answers. We've also seen how constants really matter with data sketches. Space complexity results, while nice, can yield the wrong choice of data sketch. We've also looked a little bit about how complex problems can sometimes be reduced to simple sketches, for example in the case where we're looking for optimal sampling methods for machine learning algorithms. We've also looked a little bit into guarantees and what they mean. And finally, we touched upon data privacy and its relationship to sketches. I hope this tutorial has been informative, or at least interesting to you. And if you have any questions, we'll be available for Q&A during the tutorial session, and you can always reach out to myself or to the Apache Data Sketches mailing list if you have questions. I, for one, would particularly love to hear about applications of data sketches that you've used, or problems that you hope to solve with sketches, or challenges you faced when using them. Finally, if you're interested in finding out more about sketches, or would like some references to read, I'll leave you with this list of resources. Thank you very much for your time.
Okay, so we'll take another break now. If people have any questions, I'll be happy to answer them. After the break, which I'll, I guess, make it 10 minutes, John will go over more production-related issues in the Apache Data Sketches library.
We'll be attempting to use the recorded videos. If necessary, I can do it live, but I can't guarantee there won't be background noise, like my son's piano class right now. In the meantime, if you have any questions, please, I think people can unmute themselves. Yes. You can unmute yourself to ask a question, or you can put it in chat, either way.
So we have one question from Siddharth around nice hashing libraries, which ones are fast and theoretically correct. So I'm not necessarily the best expert around this. I tend to use just Google, whatever people have suggested. I've tended to use Murmur hash 3. Though I think there was one very specific setting where Murmur hash 3 gave really terrible results. Otherwise, I've used I think City Hash, Jenkins Hash. I generally don't find it matters that much, and part of that is due to the fact that, in addition to whatever randomization you get from the seed and the hash, your data tends to also be somewhat random as well, right? There's some randomization there. And so it just becomes very hard to distinguish between like something which is a true random number generator and your hash function.
Daniel said that there's a bunch of feedback when I'm talking. I don't know why. I don't have any other recording sources I know of other than headphones. So for the data sketches library we're using Murmur 3. It has pretty good independence properties. And we've also looked at XX hash, which is newer. It runs roughly twice as fast because it produces half as many bits, which is a perfectly reasonable trade-off if you don't need 128 bits.
Out of curiosity, are most people interested in more research aspects or mostly production systems aspects of sketching? Are you like users or researchers? If you could comment in the chat, that'd be great. So for those who are interested in research aspects, I think learned from Siddharth that Jelani Nelson is also giving a talk. That'll be at NeurIPS in December. So Jelani is also associated with Apache Data Sketches, sort of advises, but he definitely brings a much more theoretical CS perspective to data sketching problems. Um,
Is this audio any better?
yeah, it's better.
Okay, I am dialed in through my phone.
Okay, so if there aren't any questions, we'll go to the next portion on production systems and a tutorial using the Apache Data Sketches library. So this section will last about 50 minutes, and then so we'll have our sort of final Q&A session after that.
John, and this part of the tutorial will focus on practical sketching for production systems. I'm assuming you've already watched the first part, which was the presentation by Daniel, who covered a lot of the theoretical underpinnings of sketches and went a little bit into how they would be used. This is going to focus a lot more on how you would actually build and use them in a real system. We will first discuss what makes a practical sketch. What are the properties of a sketch you would want to use in a real production system? Then we'll talk about sketch-based architectures. There's a progression moving from the early experimentation with sketches to actually using them in a full-on data cube. We also have a more detailed case study. We will address some of the common questions and challenges that arise when using sketches. So those include things like the subtlety of some of the implementations, how to convince people to accept approximate results when querying from sketches, what sketch you'd want to use in a given situation, and then finally some system planning questions. And then we will conclude. I'll describe the Apache Data Sketches library, which is what we'll use for the examples, and then I will jump over to Jupyter Notebook to give some actual demos. To motivate the next section, we're going to use this as an example. So imagine you are a company with a bunch of website logs. They'll have user IDs, they'll have the activities that happened, they'll have records of how long users spent on the site, when things happened. You have billions of these. They can be rows, they can be key value pairs, whatever. And your challenge is to try to analyze all of this in near real time. Traditional exact methods of querying this data end up being very inefficient. We don't actually use them anymore, but what we would have done would be you have your query engine, it goes and queries all the data that matches the parameters you have, say the date range, and then copies the data somewhere so that it can start creating a set of unique IDs. So if you're trying to count distinct IDs over some large window, the size of your query ends up being proportional to the size of your data. Processing this ends up requiring either a bunch of sorting or a gigantic hash table, either of which ends up being very slow. You can do things with streaming. They don't solve the fundamental problem for you. So just throwing the streaming system at data doesn't really buy you a whole lot. You still need something else on top of it. Applying time windows with exact counts is also problematic, and the key challenge there is that you end up needing to reprocess the same day multiple times. In the example here, so you have a 3-day moving window. Each day appears in 3 different windows. You can do a little bit of pre-processing for a single day, but to process the result for the window, you need to then combine the lists from all the days within the window. So each day ends up going into that computation 3 distinct times. Having reviewed challenges with exact methods, let's talk about the properties of sketches that we want for production use. Not all sketches are going to qualify here. Just because something is a sketch doesn't mean it's useful for practical problems. The lure of sketches, of course, is that they are small, compact summaries, so the idea of wanting a small stored size is kind of obvious. But along with that, we want them to grow sublinear in space. So this is a different notion of linearity from the linear sketches Daniel mentioned earlier. This is talking about the growth of the size of the sketch as the data stream grows. We want the sketch size to be sublinear relative to the length of the input data. We want single pass sketches. We don't want to have to store all the data and make multiple passes through it. We want distribution independent sketches. It might seem okay to make some assumptions about your data. You might know that your data always behaves according to some distribution, so you can make modest assumptions until suddenly something breaks and it doesn't. We don't want our sketches to just fall over because something unexpected happened, like a sensor broke or some major data quality issue suddenly popped up. Related is we want order-independent sketches. That doesn't mean that we're going to have deterministic sketches, but it means you don't need to worry about preparing data in some special way. You can feed data in and it's just going to generally work. Daniel also talked about mergeability. That's one of the most critical properties for production systems. And of course, all of these things are going to be approximate and probabilistic. Finally, one of the things that our experience has shown is very useful, and one of the more critical properties is mathematically proven error bounds. If you don't have this, you don't have any real way to assess how likely our sketch is to be incorrect. These are all approximate and they're probabilistic. We want things like the knowledge that the probability of a very large error is small. We want to make sure that we have some knowledge of how the error is going to work in these things. As people start experimenting with sketches, there are some common patterns that they go through in the exploration process. You can think of it as realizing a series of design wins as sketches become more embedded into the systems. And ultimately, for a large class of queries, people realize that sketching will let them have faster and cheaper systems and let them add new features that they didn't have before. But that said, there are certainly interesting queries where we don't know of sketching solutions at this point. So depending on what exactly you need to do with the data, you might end up with a hybrid where you have some raw data for queries, but you can still layer sketches on top of that and get a lot of wins. Returning to the examples we used at the start, the first place you can get an advantage from sketches is, of course, that they stay small. So they start off small, they grow sublinearly, so they're going to stay relatively small. And we're focusing on sketches that can handle data in a single pass. So you can shove all your data through a sketch. You don't need to worry about sorting anything. You don't need to worry about storing outside the sketch itself. And you're going to get an approximate answer plus or minus some amount epsilon. And that will work even on a single box. So it might not be the most efficient thing. We'll get there in a moment. But that alone provides a big win starting right off the bat. The next important step is to take advantage of mergeability. So rather than stream all the data to a single box, I can start pushing it back closer to the data. So in this case, I might have a bunch of nodes that are each reading a portion of the data, and I can start sketching there, and then merge all my results at the last step and get my final answer. We often talk about full mergeability for enabling parallelism. There are sketches out there that have a merge procedure, but you lose accuracy each time. Those are much less useful in a production context where you don't really have control of how many times people are going to want to be able to merge the sketches. The key advantage with mergeability, as using the example of distinct counting, for instance, is that you take these non-additive metrics and suddenly you can treat them like they are effectively additive. It's not literally the same compute cost as adding two floating point values, but it is vastly cheaper than trying to go through and recompute unique counts against multiple independent sets. The other thing you can get from full mergeability, for certain sketches anyway, is that you can even start doing a wider variety of set operations. Having realized that we can take advantage of mergeability like that, of course, the next step is, rather than recomputing a sketch each time you do a query, you can instead start storing sketches. So you can take your data, partition along however many dimensions you want, and store a sketch per dimension, and have that be what goes into your data mart. The sketches can now be merged by any dimension you want. Time is, of course, another dimension. And you only need to query the specific rows that you want. This might seem like it would result in a gigantic amount of data. So some of this is going to depend on your exact application. What we've found for processing web data, for instance, is that a lot of dimensions have relatively little data. So the sketches there might not even reach their capacity. You end up with this power law distribution, and a lot of sketches are actually pretty tiny. So this ends up working quite well and use a lot less data than you might expect. But you can always find examples where you will have less of a power law distribution, and some of this is what goes into system planning. We'll talk about that a little bit later on. I alluded to this in the previous slide when I mentioned time as another dimension, but time windowing also becomes much easier with sketches. Rather than needing to process each day multiple times, once for each time it appears in a window, you can instead create a sketch per day, or whatever your time slice is, and then the process of creating the sketch for the window is now just a simple merge operation. You don't need to reprocess everything from scratch each time. The other advantage is that late data processing is now really easy because you just drop it into your sketch. We'll now look at a case study involving Flurry. Flurry is a mobile analytics company that Yahoo bought several years ago. They have customers as mobile app developers. They have many tens of thousands of developers, and they run a portal so that the app developers are able to get metrics about how their app is performing. The way their system is set up is they have a streaming system that's getting constant data sent in from the apps, and they have a bunch of sketches that are running with 1 minute resolution. There's a 48-hour buffer of 1 minute resolution. The data streams into those sketches, and then you can make queries against those. So this is all able to happen in real time. The portal on the web browser will update every 15 seconds. That was done not because of a technical limit, but because it's a lot more convenient for the humans reading the pages to not have things update too frequently. You want your data to be on screen for a little bit of time before you update it. There's also an offline system that is the official source of truth. So that's a batch job that can run nightly. It processes things with 1 hour resolution, and it feeds them into the data mart. In this case, that's Druid. The offline data becomes a source of truth and replaces the online system. But of course, it can also handle late data because the online system is still able to send updates to those sketches if late data arrives. This has resulted in dramatically lower costs for Flurry. They are processing, tens of terabytes each day on their system. Before using sketches, they were consuming 80 billion virtual core seconds per month to process all their data. So not all their things are unique counting. They also provide lots of metrics around, say, time spent in the app and number of sessions, average session length per user. The daily processing would take 2 to 8 hours previously, and weekly data would take about 3 days. And there was just no way they were able to do any sort of real-time counting. So after moving to a sketch-based solution, they're able to update results with 15-second latency. And again, that was as much for human convenience as a technical limitation. And the amount of compute is about 25% of what it had been before. So again, they're doing all the other processing that they had been doing. And you can see how much of the compute was spent on trying to do unique counts across all the gigantic number of mobile devices. So these are real wins. There's a massive reduction in compute resources required, and you're getting your data faster. This is real money on the table that Flurry is able to reclaim. Let's talk about some of the common questions and challenges that people have. Next is that you need to convince people that approximate results really are okay. For that, we've found that you end up using different strategies depending on the type of role of the person you're trying to convince. So scientists and engineers, you can have them experiment with sketches to determine how accurate they are and see the other things that sketches enable. The other thing you can point out is that you have sketch error, certainly, but how does that compare with the other source of error that you're already not controlling? So that can be things like missing or corrupt data. In many cases, there will be some sampling error, even if it's implicit. If you're running, say, telemetry for a website, are you getting all the events? Well, if the problem is that a device failed to connect to your server in the first place, no, you don't have that data. So you are implicitly sampling some amount of data already. Related to that is, if you're talking about counts in the billions, does it really matter if you're off by a couple hundred, a couple thousand? Is it going to change any business decision if you're off by small amounts in very large numbers like that? Probably not. Engineers are reasonably open to that sort of argument. Product owners often are a little bit more protective of feeling like they have exact accuracy. In those cases, you probably need to start talking about some of the new features or maybe the speed gains and cost savings. One place where we found a big cost savings is reprocessing. So you find some bug in your data extraction logic and you need to revisit things. Sketches make that so much incredibly cheaper in many cases that alone has justified the cost of moving to a sketch-based architecture in a bunch of our systems. It's also useful to note that the sketches do have configurable accuracy. So there are knobs, and product owners often like being able to play with knobs for these sorts of things. Another common question is, which sketch should I use? If there's a variety of sketches that would seem to work for your query, there isn't necessarily a general answer. It's really going to depend on the system's context. So you need to think about things like the accuracy you require, the in-memory size, the stored size, the update versus merge versus serialize or deserialize speed. So it's really going to depend on the use case, what exactly you need to get out of this. So as a couple examples, if you're looking at traffic in a network router, counting the number of distinct IP addresses to detect a distributed denial of service attack, you're going to really want a small in-memory size, and things like mergeability or set operations aren't going to be so critical. So you're going to want something that's just going to take the minimum amount of RAM as you can get away with. If you're trying to do things like web app analytics, then trying to count things like distinct devices or people showing up, things like being able to operate over different time windows and apply set operations, intersections, set differences, those are going to end up being really key features. Even if you don't realize it at the very beginning, once people discover that these things are at least theoretically possible, they are going to want them. Daniel touched on this a little bit in his talk with a wider variety of sketches, but looking at what's available in the library that I work on, we have HLL++, that has a small serialized size and a small in-memory footprint. Merge speed is moderate. The problem is it has terrible accuracy if you start doing intersections, and there's really no set difference. Compressed probabilistic counting is a new thing that was developed as part of this library. It actually has the best known compressed size and accuracy combination. It beats HLL in that sense. Has a larger in-memory footprint at the moment. Merge speed is similar-ish, and it runs into the same problems with accuracy in that it really just can't do a good job on intersections or set differences. Theta sketches are larger, both when stored and in memory, but they have a really fast merge speed, and they support real set operations. So they give much better accuracy on intersections, they allow set differences, and the size increase, there's a big possible range, and that goes down to your use case, where I mentioned in practice, what we've found is that things tend to have a power law distribution. So we have a lot of really tiny sketches, and theta sketches in that case are not meaningfully larger than an HLL sketch. So there's certainly a possibility that they can be much larger, but in practice we've found the size difference is, it's a couple times larger, but 2 to 4 rather than closer to 16, which is a theoretical bound. When doing system planning, there are several key questions to keep in mind. The first is identifying what type of queries you're going to need to be able to support, because that will determine what sketches you'll need in your system. Next is figuring out the accuracy that you actually need in your system. Ideally, and this is certainly promoting our own library a little bit, you want to pick something that's going to let you change your mind later and still be able to use your historic data even after you've changed your mind. You also want to figure out, are you going to need to support real-time data? Are you going to have late data that comes in that you need to be able to handle? And finally, once you have sketches available, what new functions are you going to decide you want to be able to provide? So it's always hard to predict the future in that sense, but you have a rough idea of the types of things sketches will allow, and it is certainly worth figuring out where you want to go in sort of the medium term at least. We will move on to examples in just a moment. First, I'm going to say the examples that I'm going to present are powered by the Apache Data Sketches library. We're currently in incubation. This is very much a plug for the system that I work on. We have a bunch of people. We have sort of the core team. We have an extended team of people that we consult with regularly, including Daniel, who presented the first part of this tutorial. And we have a bunch of experience using these, both from the theoretical and practical side. We've been using them at Verizon Media for at least 7 years now. We have a fair amount of history. We do make sure that we support backwards compatibility with all these things because we have customers that rely on us. The goal of our library is to combine deep science and quality engineering to make sure that we have production quality sketches. So these are trustworthy sketches. We have robust implementations, 8 years of production use. We have robust algorithms, so that means they meet the properties I had mentioned before. So small stored size, sublinear in space, single pass, order and distribution independence, mergeable, and proven error bounds in all our sketches. We also have a bunch of characterization code, and we have that open sourced as well to make sure that other people can verify that these things are working. And if they're not, we want to fix them. We also have a number of things that have been important in practice. So as I mentioned, we have backwards compatibility. We can read stuff however far back that was created with our library. We can merge across sketch sizes. We support several languages, and we have binary compatibility across them. That comes in two formats. One is that, to the extent possible, if you give the same input to a sketch in Java or C, we will produce the same result with it. And we have a consistent serialization format, so you can create a sketch in C and then load it in Java, and it will work. Daniel described a fairly large variety of sketches. The Apache Data Sketches library does not have all of them. We do have a reasonable selection of sketches. We have several for cardinality with different properties. We have a couple quantile sketches. We would generally say for standard quantiles use KLL these days. We do not yet have the relative error quantiles in the library as of working on this presentation because the theory is fairly new. Merging was finally resolved, so we'll be working to get that in as soon as possible. We have frequent items. We have a couple sampling sketches. We have the library in Java, C++, and Python, and again, you can move the data in between all of them, and it should just work seamlessly. If you really want to read more about these, you can check out our website. But for now, let's end the slide portion and jump over to Jupyter Notebooks so you can see how these things actually work in practice. Okay, I'm going to attempt to do the next part live with screen sharing. Because it's not a video, you'll still get me, and I will be talking. With luck, it will actually work this time. I hope everyone can see the shared notebook. Let me know if everything seems correct. Okay. So you've heard a bunch about sketches, you know, a lot of different types. So we have, as I just mentioned, several of these implemented in Python. And for people who haven't seen them in action, it's kind of fun to actually get to play with them. So we have a couple notebooks. These are also available for download from the website. You can go through. This one is going to be on KLL. So we'll show feeding data in, show how you can move things between sketches, obviously merging in the process. In all of these examples, I'm using synthetic data. Two reasons. One is it's a little bit easier to know exactly what should be happening. You can apply intuition. And this way I didn't need to run things past the company sensors on what we were allowed to share. So I do assume they've already downloaded and installed the Python version of the Apache library. I don't need to demonstrate compiling libraries, I hope. So the README has information on the different sketches we have available. I can do a bunch of imports of things I'll be needing. You'll notice, you know, NumPy pandas, but also base64, because we will be saving these. So first is going to be creating the sketch, and that's really simple. But we have a parameter in the library. We try to be consistent with terminology. We have a parameter we call K, which controls the size of the sketch. That's also implicitly controlling the accuracy, the error bound as well. So size error trade-off. I can create a sketch, and then we can query it for additional information. In this case, we don't even need to create the object, and we can ask what the error is going to be. So for the K parameter of 160 or 200, we'll check, and K 160 is going to be about 1.6% error in rank, and 200 will be closer to 1.3. So we're going to use 200 for the rest of these. And next up, we will actually instantiate a sketch. So the value of k, create the thing, and then print it. We have printing a summary here, and this is mostly, some of this is debug info. Not all of it's necessarily going to be useful in many cases. So we have things like estimation mode false, because we haven't started sampling anything because I haven't fed any data into this. So we have estimation false, n is the number of points it's seen so far, and it's seen nothing. Storage bytes will tell how many bytes it will take to serialize this thing as an array of bytes. We do require some, even if it's empty, but that's mostly just a header so you know what it was. Moving on, I'm going to throw 150 points in, and we'll again look at that debug info. So here, n is 150. We are still not in estimation mode because the first level of sketch can hold up to 200 items, so we haven't needed to sample anything. You're going to have completely exact answers, but at the same time, a distribution over 150 points isn't so useful. To show what's going to happen when we actually move into sampling mode, we'll feed a lot more data in. So I'm going to create a sketch, same k. I'll create one with a larger k as well, because we can see what happens when we merge that. I'll feed in, I'll create some data, 2 to the 24th, so 16 million points. Update them, and then we can see how things look. This takes a tiny bit of time. First one, they have the exact same data, 16.7 million. We can see k of 200 versus k of 2000 with a larger sketch. They are both in estimation mode. If you've read a little bit on the theory, we have compactors, but then you get things promoting up to different levels. So the sketch with the smaller k has more levels, which sort of makes sense. It's compacted more times. The retained items, you can see how many of the items it's keeping in each case. So, we're well into sampling territory here. And the first sketch, it's retaining 645 items. So it takes 2.5K to store. The raw data is 64 megabytes. So even here, we have a vastly smaller amount of data. And with the larger one, we're using not quite 24 kilobytes and storing a little under 6,000 points. And we'll see what the difference is. So next, in order to do that, we're going to want to actually query this. So I was using exponential data here. We know what the median is. We're assuming that NumPy has a reasonable random number generator. So we're just going to compare against the exact median. So the median should be close to 0.693. And if we ask for the rank of that value, it should be close to 0.5. So what we see, we have our theoretical value, we have our estimate with k equals 200. It's actually a little bit farther off than the average case from what I've seen in practice, but not bad. The larger one is pretty close as well. And when we query for the median, we are again doing a pretty good job. So we're storing vastly fewer points. We computed all of this in a few seconds, and we're doing a nice job. Of course, one of the things that we often use a quantile sketch for is because we want a histogram. Being able to visualize things for the non-visually impaired is very useful. So we can create one from the sketch. And we also want to have some idea of how we're doing. So I do have the raw data still stored in memory here, and so we can plot against the exact value. So one important point, the sketch returns a probability mass function. The histogram computes things only for what's in the provided bins. So I ended up cutting off the tail a little bit. So If you want to be really pedantic, they are not quite doing the exact same data, but it's very, very close. So compute the PMF, compute the exact distribution, and I can plot. So the top one is with k equals 200. We can see it's very good. It's clearly following. There's a little bit of noise compared to the real thing. The sketch is in blue on the left, exacted in red on the right for each bin. And you can see that farther off in the tail, you have some bumps that are not visible with the exact, and that's basically quantization in the sketch. If we select a point, especially if it gets promoted up in the level of the compactor, it's going to have some minimum mass. So off in the tail, you get a little bit of artifacting when a point is actually kept. But overall, I mean, this is a pretty reasonable approximation considering we're doing it with less than 650 points out of 17 million. And with the larger sketch, you can see when you start looking really closely, you can see like a pixel or so difference on some of these, but it's overall very good. So both of these were very much capturing the exponential distribution aspect of this. As I noted, there's a little bit of mass near the right edge of the tail compared to the true PMF. It's all still well within the provided error bound. And given the guarantees of the sketch, this is not actually considered problematic. If you worry a lot about that, going to a higher precision sketch can help. But as Daniel mentioned, there's also a relative error quantile sketch. The theory is pretty new. Lee has actually already started trying to write the code for that for Java. And with luck, we'll get to adding that in C soon as well, which will let us get Python. So that would be what you want to go to. It will be a larger sketch, but it'll also give great accuracy off of the tails. So if tail accuracy is important, that's what you'd want. So this is all doing things with a single sketch, and that's all well and good. Unquestionably useful for lots of things. But if you're going to truly massive data, you still don't want to feed everything to your single box. And so, we talked a lot about merging. So there's a couple different ways you can do this. For our library, we make sure that we can merge different values of different sketch sizes. In this case, what I'm going to do is create one sketch with 200, another sketch with k equals 300. I'll feed in some normally distributed data, different means, -2, +2, and different numbers of points. So let's do that. Takes a second to feed everything in. Now it's done. We don't have a separate object for unions with KLL. We have two options. We can create an empty sketch and use that as the target of our merge, or we can not care and just say merge sketch 2 into sketch 1. We're going to do the latter here. So we'll do that, and we will look at our debug information. So we have 50 million points that have come through here. We're retaining 400 items. So not storing all that much. We can see minimum max values of what we've processed so far. And again, we'd saved the raw data so that we can compute the exact distribution for comparison. So compute the, in this case, is for good measure, PMF and CDF, and now let's plot those. So we had one component centered around -2, one component centered around +2. The one at -2 had half as many points. We are capturing that extremely well here. If you look at the CDF, you see the same thing. You can tell where the different Gaussians are centered. Everything looks pretty much exactly like what you'd expect. So if you're trying to do any large-scale analysis, you you need to make sure you can move things around. Maybe your system is going to work fine and communicate things internally, but sometimes you want to be able to process a bunch of stuff on a compute cluster and then pull them into Python and be able to manipulate them there. Maybe your processing is in one system and you have to send them over to something else to actually store them and query them. So transportation is important. We looked at things like protobufs, and stuff like that ends up being a lot bigger in size. And we were getting complaints from, when this was still an internal project, we were getting complaints from our data systems that storing things in those formats was just taking too much, or would take too much space. So we have well-documented serialization formats. And what we generally suggest is if you need to move between systems, you base64 encode them. So what I'm going to do here is create a simple tab-separated file with a handful of sketches loaded in as a pandas data frame, and load it back in using a pandas data frame, and I'll show how you would encode it in base64. So first, I'm going to simplify things by defining a sketch generation method function. It will know two families, normal and uniform. I'll be able to specify a number of points, a mean and variance. And the reason I'm using normal and uniform is because mean and variance are sufficient to characterize both of those. So tiny, tiny bit of algebra to get from mean and variance to my upper and lower bounds. So let's define that. And now I can have a much simpler write to file snippet of code. So I'm going to have some normal, some Gaussians, I'm going to have some uniforms, different numbers of points, different means, different variances. So this will take a moment because I have to generate all the data and store it. Okay, now we have that. If you really are interested in seeing what a serialized sketch looks like, it's going to be a bunch of not very useful gibberish because it's raw binary encoded in base64, but it's fun anyway. So trying to use this in a data cube, oops, let me go down, not back up. To load this in as a data frame, I first define a deserialized lambda, where all I'm doing is sketch deserialize and the base64 decode of the stored data, and then I'm just going to load it in using pandas read CSV. So that's fast. What you can see is I stored distribution family, number of points, mean, variance, and what you see for the sketch itself is it's printing the summary info because which indicates in this case that it's successfully read it in and is stored as a sketch object. So it's not just holding a array of things, it properly decoded it. And so now we can go through and we can start looking at queries. So in this case, I have a sketch. Actually, let's start with K. So I'm going to create a query result. So I mentioned there were two ways I could merge one sketch into another. In this case, I'm going to create a result sketch with a value of K. And I'm going to merge everything that matches my query into that. So in this case, I'm going to take all the normal distributed stuff and merge it in. So I will do that. And you can see I have, what, 71 million points in there. Storing 563 points, total things. Still tiny to store, less than 2,400 bytes still. So the raw data was 272 megs, and I can save it in just over 2K. So again, we'll come down and plot this. I didn't try pulling out the raw thing, but you can see there were 5 components here. You can actually reconstruct them. There's a tiny one here, so 1 over at -4, 1 at -2, 1 at 0, 1 at +2, and 1 at +4. This one's a really tiny blip, but it is there. What I can also do, and I can come back and I can rerun the same thing. So there's actually some advantages to merging, to using a larger merge target. So even though all my individual sketches were created of size K, if I create a query target that is larger than that, I can do this query. So it's retaining 3,200 items here after my query, which if you notice is actually more or less just all of the items from the individual sketches. I didn't compress anything further. And you might expect that I will give you some better guarantees. If you ask the sketch what the guarantees are, we tend to be on the conservative side. We didn't try to figure out what the error bounds would be in this case automatically. But by actually plotting this, you notice that things are a little bit smoother. And so it actually can buy you a little bit of extra accuracy by using a larger merge target weight. So I can pause very briefly if there are any questions. Because we're also sharing that specific tab, so I need to jump over to the other one. Okay, I don't see any. So let's move on to data. So same setup. We're going to inject artificial data here. I'm also going to include HLL for comparison. That's a well-known popular one, and we'll see strengths and weaknesses of HLL compared to theta. So we've done a bunch of characterization of Murmur 3. It has worked well for independence in the tests we've done. I know Daniel mentioned he did find at least one specific case where it didn't work so well for him. But overall, it's been good for us, especially since we do allow specifying a seed. The fun thing about having a good hash function is you can actually, for distance counting at least, you can feed in sequential integers. And that's perfectly good as for characterizing things. They don't need to be, the inputs don't need to be scrambled because a good hash function is going to handle that for you. So the big advantage for an example like this is we can do set operations, and we can do it where we know the actual overlap between the raw sets. So it gives realistic performance while letting us do meaningful comparisons. And let's ignore the typo I have in there. So again, I'm not going to show you compiling things. So it's just import and get going. We have nothing to plot, so it's simpler imports. So the basic sketch will feed stuff in with about 1 million points just to show the basic sketch operations, and can do the same with both a theta sketch and an HLL sketch, and then show the summary info. Oh, good, they both fit. So what do we have? We can see number of retained items. You can see a bunch of stuff around estimates and upper bounds. HLL is, we actually have 4, 6, and 8-bit representations. They all have the same information. 8 is a little bit faster than 6. 6 is the minimum. You need at least 6 bits. If you go down to 4, you end up needing an overflow table. So there's space versus speed trade-offs there. So just a little bit of information. More interesting in this case is querying for the actual information we care about. So I have my exact result. I can look at the theta upper and lower, upper bound, estimate lower bound, and this is the upper and lower bounds are 1 standard deviation, and then this is the relative error compared to the exact result. So what we can see is that both of them are doing a good job here. Neither is perfect, that's okay. They're both stochastic, so the fact that one is a little bit closer than the other right now is not inherently meaningful, since these should be set to be right about the same accuracy. Not exactly, but they're pretty close. So we can also serialize and reconstruct the sketch. With theta, we do have an option to compact things, which saves a little bit of space. It's storing a hash table. If you want to save space once you store things, just store the entries and don't save the gaps in your hash table. So I can run it. It's certainly larger, 55K for that. But then when I reconstruct it, I can also see that it is bitwise exact. We worry a lot about that. So wanting to make sure people are convinced it's exact as far as Python's precision will resolve. For theta, because we have a variety of different types of set operations, we use a different object for each of those. So there's a theta union object. It accepts input sketches. Doesn't care if you have different values of k. In this case, we're going to create a sketch with distinct values that partially overlaps what we have in the first sketch. So we went up through n. So here we're starting at 15/16 n. There's going to be a little bit of overlap. And then I'm also going to create another HLL sketch, but I'm not going to print all of them every time. Printing is mostly just so there's some, in this case, so you can see that it actually did something useful. It gives an idea of how fast the operations actually take. So now we want to feed things into the union. We know when we've unioned them, the exact result of the sketch of the two sets would be 31/16 n by construction. So I'm going to create the union, update it with sketch 1, update with sketch 2, same thing on the HLL side. And then I will compute my bounds and then pretty print everything. So I have my exact result, I have my theta estimate, I have my HLL estimate. And they're both doing okay. Theta happened to be really, really close with the estimate, but it still has a non-trivial error bound. It's a little bit more accurate, a little bit tighter a bound than HLL here. But in both cases, the exact result is within my bounds. And so that's the key here. They're both doing, because we happen to know the exact result here, but in general, we have to go by what the bounds are. And going by that, they're both doing fine. Sketch intersections. So for HLL, we have to use the inclusion-exclusion formula. For theta, we can do a direct intersection. So this formula might seem okay if you're just doing two sketches. As the number of sketches grows, the formula becomes more complex and your error starts to compound. So the nice thing about theta is that the operation is going to be applied to an arbitrary number of sketches. At some point, if you have too little overlap, you run into very large error bounds. And that's true of any sampling method. So there's no magic here, but we do get much better error distributions in general. So to explain it, really simple. I just created an intersection and update. For HLL, I have to use the estimate and then subtract so the HLL result was my union from before. I have to subtract that out. So with an intersection, if you haven't sent anything in, there's no result. So there is a way to check and just be completely sure that there really is a result in your intersection. Otherwise, we have that. And so I can come down. So remember we had the second sketch start at 15/16, so 1/16 and overlap. So again, we know our result. Here we have the exact result. We have the theta estimate, which is very good. We also have an error bound. And you notice that this ±1 standard deviation is a wider range here, but we have that estimate. By contrast, HLL is significantly farther off, and there's no super obvious. I imagine the statisticians here might be able to come up with a reasonable way to find bounds, but they're definitely going to be worse than the error bounds we get from theta. So we have, this is where the size versus error trade-off comes into play between sketch families. HLL did a great job when all I was doing is unioning things. Once I need to do other set operations, HLL has a lot more trouble doing anything as useful. And that's where the minimum value type sketches in general, that family tends to shine. So we also have set differences. Unlike union and intersection, our API is evolving slowly over time. Right now, the A not B operation is not stateless. So, sorry, is stateless. So we just create an object and we send in two sketches. So we have our item. The first item is A, second item is B. So A not B. And then we can put the result. So by using the same sketches as before, and -1/16 is 15/16, so that's our estimate. And then we can rearrange the inclusion-exclusion formula for HLL and come up with our best effort there. And what we see, we have our exact result. We have our theta estimate, which is again very good. We have our error bound. HLL is less far off than with the intersection, certainly. But again, we don't have an error bound. And actually, at 1 standard deviation, theta's error plus the standard deviation is still lower than HLL's entire estimate here. We do have a few other sketches available in Python. I don't have a pre-made notebook, but if you have questions, I'm happy to answer them. Otherwise, so this is the end of the prepared stuff. Want to thank everyone for joining in and listening. We look forward to hearing any questions you may have. And yes, there was a question in the channel that our volunteer already answered. The notebooks are already available. From the tutorial website. I might even go through and fix the typo I noticed.
I think there are two earlier questions as well, something about time series. I don't know if the example with aggregating over multiple days or time slices sort of answer that type of question. There are also other ways to kind of deal with time, which deal with sort of these dyadic expansions. You treat these as these queries over ranges, and some sketches like the count sketch are particularly good for that, where you just break intervals into like 1 day, 2 day, 4 days, something like that. And then you can insert things in where you only need to query like a logarithmic number of entries. So there are a few things to deal with time specifically, but yeah, most commonly you just see with distinct counting 1 sketch per day or 1 sketch per time slice, and then you aggregate that way. I think there was one other question about what sketches to choose. I think Yeah. If someone wants to re-ask that question with a particular scenario in mind, we'd also be happy to answer that. Oh.
Okay, this is a feature request for the library, specifically asking for a count min or count sketch. We have been looking at that. One thing that we've had a request for is sketches that can support deletions. So the existing heavy hitters algorithm doesn't do such a good job with removing things. Count sketches, I think count min would have more trouble with that, if I remember correctly. Then you might have a comment there. But I know the regular count sketch can definitely allow deletion. Okay, yes, confirmation in the channel.
Count min also allows for deletion. Just you need to make sure that your deletions are not greater than your insertions. So.
So one of the challenges that we've thought of is, so the object itself, the sketch object is easy to do and you can do it pretty quickly. But then querying things afterwards becomes, does require significantly more machinery. So the actual object, if you know it's there, you can query something and get a count. If you just have the sketch, you just have, say, a count sketch, there's no way to say, tell me what items are in it, unless you have unless you've been storing something, keeping track of that. And obviously you can, if you have a finite universe, you can just query through the entire universe. But if you're dealing with strings, that becomes a wee bit of a challenge to loop over every possible string and see what's in there. So that's one of the things we've been debating, how we can do that efficiently. Even with the existing heavy hitters sketch, it became something of a challenge finding a way to manage all the items efficiently enough. They started to bog down, and so they ended up coming up with a new reverse purge hash table. And I don't remember the details of all that offhand. And even there, we've ran into some really subtle implementation things where in the merge process, it ended up, so the hash table in general requires an assumption that things are evenly distributed throughout your hash table. And we found out we were violating that. And the front of the hash table was pretty much completely full. So at the end, it was still more sparse, but it was slowing down because it was having to start probing and go a really long way on every single item. We ended up doing, what was that? Golden ratio based probing ended up actually solving a bunch of this. You end up iterating through all the points, but you do it randomly enough that you do it effectively randomly enough that it worked well. It was a pretty nice solution, but yeah, we ended up doing a bunch of simulations of why it was slowing down, and this is where the implementation subtlety comes into play that I had mentioned earlier.
And I also think that one of the reasons that I guess the count sketch or count min sketch hasn't been implemented yet in the Apache data sketches library is like there hasn't been a super clear use case that people have presented, and so like I think if there's a super clear use case, then that makes it much easier to get prioritized. I guess the Apache data sketches has been trying to focus on like different systems which people are using and trying to make sure that people will adopt it before including a sketch. But certainly, count min sketch and the count sketch, they're kind of the basis for a lot of other sketches as well. So from a theoretical perspective, they're very nice.
They're very much on the short list of things we want to implement. If anyone is interested, we are happy to provide feedback on your code and help get it into production shape if you have a prototype. We are an open source library, You can contribute. We're thrilled to get contributors. Please contribute. So the other sketch that Daniel mentioned, almost knocked my phone off the table. The other sketch Daniel mentioned that we feel like has a lot of potential that's still untapped is frequent directions. We've had an implementation in Java for multiple years. We just haven't found a good way to use it yet. We have an intern who's looking at regression with it and trying to improve things. But one challenge we've had for making it practical is that the error bounds are ultimately on your sketch reconstruction error. You know, it says that your covariance is going to be close to the covariance of the raw data. And this is a really useful property mathematically. But when we've had ideas on how to do it, I have no clue how to explain this to a non-mathematical product owner of what this buys them. Because they're thinking in terms of what actually happens with the data, not is the covariance close. So things like you can, at a basic level, the fact that you can arbitrarily flip the directions in your matrix and have the, you know, if I multiply directions by -1, things are still going to work. But I'm going to get very different results from running a projection against that. Consistent, stable outputs matter a lot for most practical applications of these things. So we haven't yet resolved that. I feel like this should be a really useful sketch. And it's very frustrating that we haven't gotten anywhere.
Yeah. And the last, the other class of sketches which Data Sketches hasn't implemented are set membership sketches. So we didn't talk about that so much in this tutorial, but there's also these sketches which grow linearly in size with your data, but just have a very good constant factor. And that those allow you to test whether or not some item is in some set. So for example, they're often used in, for example, like maybe caching scenarios or like testing if like you need to make a disk access, something like that. So it tries to save an expensive operation. You test whether or not something is in your data, and then if it is, it's guaranteed to return yes. If it isn't, it may return yes or may return no, just yes with small probability. So there's a small false positive probability rate. And so that's sort of another area which yeah, if people have a good use case, can make a convincing case, then I think like Data Sketches would be very open to including it. So in that case, there are existing use cases. I just haven't convinced Data Sketches to use.
There's a little bit of reluctance from some people to include things that grow linearly with data, which doesn't mean that there aren't very practical uses for them. So that's what Daniel's referring to with having not convinced people yet. Check the off chance there's anything in other chats. It appears no.
So we'll wait until 4:30 if there are no other questions, and then yeah, feel free to reach out through whatever means, through email or whatnot, if you have questions after the tutorial as well.
Yes, and we definitely would love to hear more about if you have use cases, particular use cases, maybe outside of, say, web analytics as well.
At some point, just as a demo, I got Quantiles running on my phone. I just made a simple Android app. And that worked pretty well. We haven't found a particularly compelling use for it in that you'd have to run it for a really long time for it to be helpful. It would reduce data versus sending things over the wire. But for most of the reasonable things we found, it would be things like, frame render times. So you could report back occasionally a relatively small number of points, because it turns out telemetry ends up being very expensive on a phone. And even on our backend systems, the telemetry data gets, if there's too many calls, it becomes a significant amount of processing time on our front-end servers. But for things like page render times, if you're doing it in, unless you need arbitrary precision, you have a pretty good idea of the range of values, so you can just have an array of fixed size and increment. So non-sketching solutions end up being close, it might be a little bit larger, but it just doesn't buy you a whole lot in most cases.
Yeah, so that's generally sort of one point about sketches, which is that if you need to adapt to your data in some form or fashion, the sketches can be quite useful. If you have a very specific problem where you already know what your data distribution is like, a simpler approach can work quite well.
Yeah, so the data independence is an important part of why these are useful. I suspect in-person tutorials would end up having a slightly more vocal audience.
Okay, so since there are no questions, I guess we can go ahead and wrap up. We just want to thank everybody again for their time. Sorry again for all those technical difficulties in the beginning. Yeah, and we'll upload sort of updated versions of the video as well to make sure there aren't any hiccups. So thanks again, everybody. Hope you have a good rest of the day. And thanks, John, for doing this tutorial with me.
Thanks, thanks.
Thank you.
I just unmuted myself to just at least once we can have a vocal kind of thing. Thank you, thanks both of you.
Yeah, thanks, Siddharth. Thanks for helpful comments and questions.
Yeah, farewell.
Okay. Yes.
Okay, I'm going to end the meeting for everyone because we ultimately need to turn this back to KDD. So that'll, let me stop recording. And then I'm going to end the meeting for everyone since KDD is reusing Zoom meetings to limit the number of licenses.